So first of all, I'd like to welcome you all to the next GSQ and UQ collaborative webinar for May. And we have a really fantastic lineup of international speakers this month. So really appreciate all of them being in attendance. I'd like to pay my respects to the traditional owners of the lands on which we gather, both within Brisbane, within Queensland, around Australia and around the globe. Pay my respects to the First Nations elders, past, present and emerging. Now, today is our Global Collaborations webinar, and we have speakers from 8 different countries. We have New Zealand as a near neighbour. Very excited to hear what they're up to. We have Kamiya-san from the Japan Oil, Gas and Metals National Corporation. Thank you, Kamiya-san. We have Simon Michaux from GTK in Finland, and Pak Hilman joining us from the Geological Agency of Indonesia. We have Lesley Wyborn, Honorary Professor at ANU here in Australia, Australian National University, who's going to talk about some of her collaborative work, international work. We have, I know that we had your name wrong in the agenda, Kari Aslaksen, is that right? I'm sure I messed it up somehow. Head of the Mineral Resources section at the Geological Survey of Norway, which I'm excited to hear about because I did my PhD in Norway with the help of some of the NGU geologists. So that one feels very special to me. We also have Garth from the USGS, who's going to talk to us about the Critical Minerals Mapping Initiative, which is a collaborative effort between the Australian Geological Surveys, the Geological Survey of Canada and the USGS. So Garth is from the USGS. He's giving us a pre-recorded talk, but may join us for Q&A. And if not, then Dave Houston from Geoscience Australia will field questions. And then last, but definitely not least, we will have Roger Hamburg from the Geological Survey of Sweden. And he's not here as a panelist just yet. He's going to join us a little later on in the session. So without any further ado, it's my great pleasure to introduce Rose Turnbull from GNS in New Zealand, who is going to talk to us about critical mineral resources in New Zealand, current state of understanding and work in progress.
Great, thanks, Helen. I'll just share my screen and get that process going and put that up, and hopefully that will pop up in a second. But kia ora everyone, while I'm waiting for the screen to pop up. I think it's going to pop up.
It's sharing now.
Today I'm going to be presenting on, is it sharing? Yep, okay, here it goes. It's just having a moment while it comes up. I'll bring that down there. There we go. Put that one down there. Yeah, okay. Can everyone see my screen?
Yeah.
I hope so. Awesome. Okay. Kia ora everyone. Good afternoon. As Helen said, I'm from Geoscience, which is New Zealand's Geological Survey. And I'm going to be presenting on behalf of a team of us who have been working in the critical minerals space in New Zealand in the last couple of years. Just presenting some of the work we've been working on, which is primarily desktop-based, based modelling of the critical mineral potential for rare earth elements, lithium and nickel cobalt in New Zealand, and highlighting some of the steps we've taken and the results from our work. I'll also touch briefly on some of the issues faced with mining in New Zealand, some social licence to mine work we're also in the process of undertaking, as well as the New Zealand government's position on the minerals industry in New Zealand. And before I'll just say thanks to my colleagues Matt Hill, Regina Morgenstern, Phil Glassian, Lucian Siskowski, who's been working on this stuff in the last few years with me. So like elsewhere in the world, in response to an impending global climate emergency, the New Zealand goal of being carbon neutral by 2050. Among many of the ways to achieve this is by increasing our renewable electricity production to 100% renewable by 2035, as well as the adoption of new innovative energy technologies and the electrification of our transport system, which presently accounts for 21% of our total carbon emissions. And at the moment, only 1% of our transport networks are fueled by clean electricity. Importantly, in order to achieve many of these objectives, is the need for critical minerals. And currently, New Zealand imports all its clean tech components. No critical minerals are currently mined or produced in New Zealand. So as we all know, the global demand for the minerals required in clean energy technologies is predicted to grow by 4 to 6 times in order to meet countries' global climate goals. So much of this demand is in the metals required for electrification of energy and transport networks. One of the problems that the world faces, which is becoming increasingly apparent in this current time of global political uncertainty, is that only a handful of countries control the supply of both the mining and processing of these critical minerals. And many of these countries actually have poor health and safety and environmental regulations. So the question therefore remains for New Zealanders is what should New Zealand be doing to support the sustainable and responsible development of minerals to support our transition and to sustain it as a carbon neutral economy by 2050. We do really well in the generation of renewable energies, but should we and could we be producing some of our own clean tech minerals and products? Should we be relying on importing all of them? But first, for those of you unaware of where New Zealand sits in a global geological context, this is a reconstruction of Gondwana supercontinent, or part of the Gondwana supercontinent, the bit that I'm interested in, which is New Zealand, at 85 million years. So this is the North Island, the west coast of the South Island, and the east coast of the South Island prior to its current plate configuration with the Alpine Fault running through here. So New Zealand was once part of the Gondwana supercontinent, lying off the east coast of Southeast Australia and eastern Antarctica. And our basement terrains were formed along this active Gondwana margin between 500 and 100 million years ago. And this past Gondwana tectonic setting, as well as our current unique setting across an active plate boundary, has influenced the mineral wealth of New Zealand. So several similarities exist between southeastern Australia and western South Island of New Zealand, with plutons, Phanerozoic plutons emplaced during the Gondwana subduction-related magmatism, and their associated mineralization being gold, moly, copper, and tin. And we also have some mafic and ultramafic intrusions in place during this time too, that have resulted in nickel, copper, and platinum group element mineralization. In the west coast, the east coast of the South Island down here near Dunedin, we have a world-class gold operation, the Michaux gold mine, which was formed during the Mesozoic as a result of orogenic events, and it also has associated tungsten as well. And recent and active volcanism in the central North Island, associated with our current subduction margin, is currently creating and has created, just in the recent past, younger deposits of copper, epithermal gold, and also rhyolite-hosted lithium deposits are a potential there, as I'll discuss. So currently there are only 3 mineral commodities mined in New Zealand, which seems crazy when I'm talking to countries that have, I don't know how many different types of mineral commodities being mined, but the 3 that we actually mine in New Zealand are gold, silver, and iron sands, which are used in the steel manufacturing industry. Coal is also mined, but in increasingly smaller quantities. And the rest of the mining practices in New Zealand is restricted to the aggregates industry. And in comparison to our lovely neighbours in Australia, who in the year 2019-2020, the financial year, earned $15.2 billion in state and territory royalties, our comparative royalties are very, very tiny. And this is a function of the fact our minerals industry is pretty small. The minerals mining, one problem we face in New Zealand is that because we've focused so much on traditional minerals, such as coal, gold, and iron sands, our knowledge of where we might find other prospects is actually limited. We do, however, have an excellent understanding of our geology, and historically, mining for other minerals, including copper, tungsten, chromium, and tin, has occurred in the country. And furthermore, there is an interest from mineral exploration companies to look for minerals other than the big three in New Zealand anyway. For example, exploration permits have been granted to several companies that are interested in rare earth and garnet mineral sands along the west coast of the South Island, as well as lithium deposits in the central North Island, which is becoming important based on some of the work we've done just a couple of years ago. And we also have the potential to undertake byproduct or processing of tungsten byproduct as part of the gold mining operation at Michaux. There's also been some research to look at silica sand deposits and platinum group element deposits down in Southland. So in order to fulfill the data and knowledge gaps in the critical mineral space, Geoscience was commissioned by New Zealand Petroleum and Minerals in 2018 to undertake mineral potential modelling for 3 different commodities, these being rare earth elements, lithium, and nickel cobalt. And New Zealand is really well placed to undertake these types of mineral potential studies. We have significant databases that enable mineral potential modelling to be undertaken. These include regional geophysical databases. Oops, hold on, I'll get the laser pen back. Such as these, which are covering areas of the most highest mineral potential. And in combination with that, we have regional soil geochemical surveys that also correspond with many of these areas that have been covered by geophysical surveys. We also have a lot of databases housed by Geoscience, including the 1 to 250,000 geological maps that cover all of New Zealand, and also the PetLab database, which is an online database that houses over 210,000 records, sample records, of which over 66,000 have associated analytical data, which can be used in our mineral potential modelling projects. So these studies, the mineral potential modelling projects that we've undertaken are useful as they provide a framework for undertaking similar studies on other minerals. And this is important when we think about what the definition of a critical mineral is, because with changing and rapidly evolving technology, what's deemed critical now might not be deemed critical in the future, and vice versa. Minerals that aren't so interesting now might become critical in the future. So as I've said, this project was funded by New Zealand Petroleum and Minerals, which falls within the Ministry of Business, Innovation and Employment and is responsible for administering the Crown Minerals Act for the New Zealand government. And as such, it regulates prospecting, exploration and mining activities on the Crown estate and private land as well. So this jointly funded study was largely desktop based, although some geochemical analyses were undertaken, and it was focused at a regional scale to identify areas of high potential and allowing us to rule out other areas based on our current knowledge and data. So the colours here, for example, in the reds and the oranges, identify areas of high mineral potential. The blue areas are low mineral potential, but these could be elevated with the acquisition of more data. And in the grey is areas that we would rule out based on them not having the right rock type or various other mappable criteria, as I'll discuss. So these things are great. They provide a framework for us to undertake other commodity studies that we haven't looked at, such as copper, platinum group elements, and tungsten. So our mineral potential modelling followed the mineral systems approach, which most of you are probably quite familiar with, whereby key components of a given mineral system are recognised that are crucial for the formation of ore deposits. So this is an example where we were looking at rare earth element mineral potential using our mineral system components along the top here: energy source, fluid ligand and ore source, enrichment and focusing mechanism, trap and surface expression. And this was done for a deposit model based on hard rock rare earth elements. So within this, we have various mappable criteria that we can map within a GIS system and then use expert weighted fuzzy logic spatial modeling to create our mineral potential maps that can go into creating our final mineral potential model. This is an example of the mineral potential model we produced for lithium. So this model was actually a combined model based on the fact we didn't have that much knowledge of where lithium was in New Zealand or where it might be. So we combined it on the basis of looking for pegmatites and also for lithium hosted in hydrothermally altered lake sediments. And in the next slide, I'll explain what that deposit type is. This is our mineral system-based lithium mineral potential model, where we put in different mappable criteria for our different mineral system components. And then we produced our mineral potential models. And what we can see here is that even though it was a combined model, we still did pick out areas that did show elevations that made sense to us from a geological perspective anyways. In the reds and the yellows areas on the South Island's west coast, where we know we have a lot of granites that have evolved crustal compositions, which is the perfect place to find pegmatites of the right composition to host lithium. And then it also highlighted areas in the central North Island, the Turnbull volcanic zone, where we are looking at this model for hydrothermally altered lake sediments. So on the basis of the results of this, New Zealand Petroleum and Minerals, or NZPNM, gave us a bit more money to actually undertake a follow-up study looking specifically at this model for hydrothermally altered rhyolites within a sediment-hosted deposit. So this deposit type is a new and emerging deposit type, and it's related to rhyolites being erupted from large calderas and then being deposited back in those calderas into lake settings, where they're then hydrothermally altered and enriched in lithium as a result of continued hydrothermal circulation, typically along the boundaries of these calderas, which are fault controlled. So in this lithium mineral, keeps doing that. In this lithium mineral potential model, we added in a bunch more of our mappable criteria for our mineral system components. So these included the geochemistry of geothermal fluids and also groundwater that we could get our hands on, the location of calderas throughout the topovolcanic zone, the location of paleo lakes, also at 3D, so not just the surface location, but also mapped out at depth based on drill hole data that we had. And also we took a bunch of samples of lake sediments from historic drill core throughout the topovolcanic zone and analysed them for lithium and also pathfinder elements. And this was because most of the hard rock geochemistry undertaken in this area wasn't analysing for lithium or some of the other elements that might help us to find these types of deposits. So when the model was run, this is our 2018 model, which was our combined model, versus our 2019 model, which was specific for the deposit type in the central North Island that we were hypothesizing. You can see that the difference, that additional data, geological understanding, and a focus on one deposit type has shown to highlight the lithium mineral potential in the central North Island. Interestingly, one sample had very, very high lithium, and 31 samples out of the 189 that we analysed had lithium values higher than 200 parts per million. And following publication of our model, several exploration licenses for lithium have actually now been taken out in the topovolcanic zone. So what is the New Zealand Government and Regulatory Authority, NZPNM, doing in the critical mineral space? Well, they recently in 2019 published a 10-year resources strategy for New Zealand that identifies the government's priorities and a long-term vision for the mineral sector. It does address the role of critical minerals in this energy transition, but it's a bit vague about what that is. And one of the interesting things is that throughout the entire strategy, the only 3 critical minerals that were mentioned were the 3 that we undertook the studies for: rare earth elements, lithium, and nickel cobalt. So I think if we were able to secure funding to undertake more of these types of mineral potential studies, we would actually find we have the potential for other critical minerals within New Zealand, and they also might become part of the government's resources strategy. One of the biggest things that this strategy covers is social license to mine, social responsibility, and community engagement. And public perceptions and the social license to operate are essential to consider, even when we're talking about critical minerals. So in New Zealand, as I'm sure it's the case elsewhere in the world, there's a lot of really emotive and negative words often associated with mining in the press. Some of it is definitely valid based on past mining practices, but not all of it. And if we want to shift to a clean tech, carbon neutral future, then minerals are an important part of that. So to examine the social side of the equation, scientists at GNS are undertaking a study in the Coromandel, which is this part of the North Island of New Zealand, just southwest of Auckland. And it's a place that's popular with holidaymakers, retirees, alternative lifestylers, and other people. And so it has got a perceived anti-mining sentiment. However, no independent representative surveys have actually been completed. So our current project is looking at copper in the Coromandel as a case study to review our potential copper resource. These yellow dots are where we know we have copper. And in the green is our conservation estate. Just to note, Waihi is an active gold mine down here. And surveys of the public in that area are also going to be undertaken to understand social perceptions of mining in this affected community. And one other space that we're getting into is the critical mineral extraction from geothermal fluids, which has the potential for a renewable mining industry, which is one powered by clean geothermal energy, on-site processing, and re-injection of depleted fluids back into the ground. So Geoforte is a company that's currently operating at one power station in the central North Island that's already extracting silica and is in the process of setting up a pilot plant to extract lithium. And at GNS, we're looking at analysing a bunch of geothermal fluids to understand actually what other critical minerals or elements exist in our geothermal fluids, because many of these aren't actually measured and we don't actually know what potentially we could be extracting from them. And the potential could be huge. So for instance, at one geothermal power plant, which processes 30 million tonnes of geothermal fluids annually, just by taking the lowest amount of gallium measured in one of those plants of 0.2 parts per billion, this would equate to 6,000 kgs, 6,000 tonnes of, 6,000 kgs of 6,000 tonnes, of gallium passing through that geothermal power plant annually, and it's 700 New Zealand dollars a kg. That equates potentially to a $4 billion resource. I mean, you've got to extract it and the technology to extract it, but there is potential for extraction of other elements from geothermal fluids. So just to summarise, our mineral potential modelling work has highlighted that New Zealand has the potential to host several critical minerals, although a lack of funding for research into our critical mineral potential does hamper industry investment and exploration in this space. So if we don't know what we have, who's going to invest? As a country, we haven't yet compiled what minerals we consider as critical. We don't have a list of critical minerals. We just seem content on importing all minerals required for our just transition. Is this ethical? And there are many barriers with vocal anti-mining sentiment, and more work needs to be done regarding the social licence to mine. However, we do have many advantages with the development of a critical minerals industry. We have the ability to mine and process minerals in a sustainable and renewable manner. We have an excellent geological framework, which reduces site selection risk and enables more targeted exploration. And there is the potential for us to develop innovative ways of extracting minerals from geothermal fluids in an environmentally friendly way. And one other thing that we could potentially be doing is processing more critical minerals. So this is the Tiwai aluminium point smelter, which imports bauxite from Australia and processes it using 100% renewable energy from a power plant that was built for this specific purpose. It actually produces 15% of New Zealand's electricity. So could we be doing more in this space with our renewable energy resource? And I'll leave it at that. Thank you.
Thank you so much, Rose. That was great. And I know that we have quite a few comments and questions in the chat. And I've been jotting down ideas to get in touch with you later as well outside of the webinar. So obviously really thought-provoking, and a lot of people enjoyed that. So I do have a question from Anita Pabak-Box, who works a lot in mine waste, critical minerals in mine waste. She is asking, what opportunities do you see for secondary prospectivity or mine waste as a source for critical minerals in New Zealand? She's hoping that you can expand on comments that you made during your fantastic PowerPoint.
Thank you, Anita. Yeah, so I did touch on it slightly in that the gold mine at Michaux does have a significant amount of tungsten in it. So there have been PhD studies from Otago University that have looked at the tungsten, and there is potential for that to be developed and processed as a tungsten resource. So that would be one possibility of mine waste being used. And I do know on the West Coast, the New Zealand Minerals Institute, which has been funded by the government as a research institute, has set up to be looking at processing of waste from rubbish dumps and things like that. If they're looking into innovative techniques to try and process some of those and other things, mineral sands as well. But they are looking, I think, at waste from human waste from dumps, rubbish dumps, to process for certain elements as well.
And you also mentioned the gallium in the geothermal power stations too. So.
Yeah. So that's one. I mean, that stuff we don't know that much. This is a project that my colleague Lucian is working on at the moment to analyse what actual metals exist in geothermal fluids. Most that get analysed are the ones that aren't that interesting from a critical minerals perspective. So we want to understand what actually is there, what quantities are there, and then what techniques could we develop to extract those. So we've got this circular process going on, generating electricity, but also pulling out some of the metals as that happens.
And John Menzies has also made the comment in the chat that the Taupo volcanic zone, he's not surprised about the potential for lithium, and he says there are a number of other similarly prospective modern volcanic environments with similar potential, but they're all challenging from a permitting perspective, so that community and environmental aspect.
Yeah, well, the interesting thing with metals, the interesting thing with metals in the geothermal fluids is that the legislation is very murky. There actually isn't any legislation in New Zealand that says who that belongs to. So the councils don't have any control, and the government, New Zealand Petroleum and Minerals, don't have any control either. So there's a very murky, which is currently being worked out by some of these councils as to how this process will work, what type of permits are needed. At the moment, there are none. So it's a bit of a free-for-all if people were going to get into it. Yeah.
I have one more question as well from, oh no, I hope I pronounced this name right, Xing Yi, who says, what is the specific technology applied to extracting rare earths from geothermal fluids in New Zealand? For example, is it solvent, is it microbial metabolism, or an electrochemical system?
We haven't actually tried to extract the rare earth elements yet. That's the work in progress that Lucian hopefully is going to work on in the next few years. I can't say what the process is to extract the lithium because I think that's proprietary to Geo40, but they do, I think it's called a GeoSieve or something. They've got some special process with that they're extracting the lithium from. But we're hoping to work with companies like that and others internationally to develop those techniques in New Zealand. But first we've got to find out how much rare earths we actually have in our geothermal fluids. And
Manthan Narendrakumar Varia is also saying, what is the future prospects of the mineral industry in New Zealand for battery minerals? But I think that that's what you've covered throughout your talk. So perhaps we'll just encourage them to relook at the recording if that's possible later. So we might leave it there, Rose, so that I know Evan will keep us on time. He's already texting me saying, hurry up, move to the next one. So thank you so much. And if there are further questions for Rose or any of our other speakers, please hang around at the end of the session because we do open up then to a more general discussion. Rose, you might have to go and pick up your kids, but if you put questions,
we'll try and make it back for the discussion. Yeah,
that would be great.
Otherwise, I'm happy to answer by email later.
We can compile questions and email them to you later, and then share them with the group. So thank you so much. Really appreciate.
Thanks very much, everyone.
From across the ditch. It's great to have you involved.
Thank you.
All right. Next up, Taro Kamiya-san from JOGMEC in Japan. I love that you are able to join us, Kamiya-san. He is the General Manager for the Metals Technology Centre at JOGMEC, and he's going to talk to us about JOGMEC's activities and cobalt recovery research in Queensland. And this is a collaborative work between the GSQ, JOGMEC and UQ. So very excited to have you on board, Taro-san. Thank you.
Thank you, Helen-san. So I will share the presentation. Can you see my slide?
Yes.
Yes.
We can see it.
Okay. Okay. So I will check. Good afternoon, everyone. My name is Taro Kamiya from Japan Oil, Gas and Metals National Corporation. And JOGMEC, Japan Oil, Gas and Metals National Corporation, is a governmental organization, and it was established for stable supply of natural resources to Japanese industry. And as Helen-san said, we started a research with the Geological Survey of Queensland and the University of Queensland last year, which is on recovering cobalt from copper mine tailings. Today, I'd like to introduce the research as well as our activities. Yeah, Japan Oil, Gas and Metals National Corporation, JOGMEC, is established in 2004. And the field of our activities are ranging from oil, gas resources, mineral resources, mine pollution control, and also coal mining and geothermal resources. And also we operate stockpiling facilities in Japan for oil, natural gas, and rare metals. And we have overseas office in 13 countries, and in Australia we have office at Sydney. This slide shows the JOGMEC activities in the field of mineral resources, which cover most of the mineral resources business from exploration to development, recycle, and mine pollution control. I have been working for the technical research of mine development and recycle and mine pollution control. Like New Zealand, in October 2020, the Japanese government declared its goal of carbon neutral, which means that overall greenhouse gas emissions will be zero by 2050. Here, carbon neutral declaration. And JOGMEC has been taking initiatives for achieving sustainable development goals since before, but in response to the government's declaration, JOGMEC has decided to further strengthen the efforts to realize a carbon neutral society. And last year, JOGMEC announced its carbon neutral initiatives. JOGMEC has a wide range of activities, as I said, so we have a lot to do to contribute to achieve carbon neutral society. In the metal section, our focus is stable supply, which are necessary for electrification. Especially demand for metals to be used in electric vehicles and renewable energy power generation facilities are expected. Like lithium, nickel, and cobalt, and rare earth metals is the most necessary metal for us. This is the reason why we started the cobalt recovery project research in Queensland. Let me introduce Metal Technology Center of JOGMEC, where I worked, where I work as a general manager. The center is located in Osaka town. It's a northern part of. It is located northern part of Japan, from about 650 kilometers from Tokyo. Tokyo is like here, and the north part of Japan. And we are carrying out these three researches: treatment of refractory ores, new extraction and recovery technology, and passive treatment technology of acid mine drainage. From the next slide, I'd like to explain passive treatment technology developed by JOGMEC. In Japan, nearly 6,000 mines were developed, but now only one is currently operating. Out of these abandoned mines, mine drainage has been treated at 79 sites, and it costs more than $40 million per year. For cost saving, we have been researching the applicability of passive treatment system to abandoned metal mine sites in Japan. Acid mine drainage from metal mine in Japan contains not only iron, but also zinc, copper, cadmium, and so on. So we researched the process using sulfate-reducing bacteria for removing metals at sulfide. Yeah. There are some treatment cases using sulfate-reducing bacteria in other world, but this process needs a lot of time to remove metals from wastewater. So a large area is needed to have enough time to treatment. But in Japan, most of the abandoned mines are located in the mountains, like this photo. So our challenge is to establish a process which can complete the reaction in shorter time. This is our solution: rice husk and rice bran. We produce rice all around Japan, and the waste material is discharged when rice is polished. Rice husk is shell of rice, and rice bran is between rice husk and white rice. Rice husk is used as substrate of reactor. Rice bran is used as mainly organic, rice bran. No, sorry, rice bran. I'm sorry. Rice husk is used as substrate of reactor, and rice bran is used as mainly organic source for microorganisms. Rice husk and rice bran are agricultural waste in Japan, so we can get easily at everywhere with low cost. Rice bran is high effective organic source. In other words, rice bran is easily decomposed to low molecular organic acids by many kinds of bacteria. In the process, rice bran is filled up on the upper part of the reactor, and the bacteria decompose rice bran to organic acids. And then at rice husk area, organic acids are supplied to sulfate-reducing bacteria, and the sulfate-reducing bacteria reduces sulfate to hydrogen sulfide ion here. This is the mechanism of the heavy metal removal with sulfate reducing bacteria. Sulfate reducing bacteria decompose organic materials and generate organic acids such as acetic acid. And organic acid activates sulfate reducing bacteria sulfate respiration. Then sulfate reducing bacteria reduce sulfate ion into hydrosulfide ion by sulfate respiration, and metal ion reacts with hydrosulfide ion and precipitate as sulfide. We have been carrying out full-scale tests since 2020. The throughput is 100 liters per minute. This is a full-scale test facility. This facility is located in mountains too. And another challenge is the cold weather in Japan. The water temperature kept around 10 degrees in winter, but we could treat the drainage in such a low temperature. Last, I'd like to explain the cobalt recovery research with Geological Survey of Queensland and the University of Queensland. It is known the copper mine around Mount Isa area. The copper mine around Mount Isa area have cobalt, but it wasn't recovered, so it was discarded to tailings. So we started the research to make the waste material to be a new resource of cobalt. The target mine is Rockland mine, and our approach is mineral processing like flotation, followed by pyro or hydrometallurgical extraction. This figure shows the model mineralogy analyzed by MLA. Cobalt exists in pyrite, and there are a lot of iron oxide. Yeah, iron oxide. So to remove iron oxide, we tried to remove iron oxide with a magnetic separator. This is a result of magnetic separation. We removed around 60% of iron to magnetic product, and while over 90% of cobalt remained in non-magnetic product. Then we carried out flotation tests with the non-magnetic product. The experimental conditions are here. We did the test with some dosage of activator, copper sulfate. These are the flotation results. With 30 kilogram per ton of copper sulfate, we had the best cobalt recovery, but it was still below 60%. Then we did MLA analysis for tailings and concentrate, and we found that the fine pyrite particles doesn't float, remained in tailings. So this is why we couldn't get high cobalt recovery. We couldn't recover fine cobalt pyrite particles. So the research so far on the cobalt recovery. The conclusion is the treated field sample used for flotation indicated that lower copper sulfate gave higher recovery for cobalt. And MLA result indicate that pyrite is highly liberated. However, most of it goes to the tailings fraction as fine particles. And next step for this research is to increase in recovery of fine particles, pyrite particles. We are planning to use column flotation test or carrier flotation test. And then when we got enough pyrite from the tailings, we will try to extract cobalt from the pyrite concentrate using such electric furnace or like something like that. And in the future, I hope that the cobalt recovery method we may develop would be applied to not only rock grands, but also to other tailings elsewhere in Australia or in other world. Thank you very much for your attention. This is my end of our presentation. Thank you very much.
Thank you, Kamiya-san. We really appreciate that. I really love the example that you showed, which I thought was very, very circular economy. So using waste from another area, the rice industry, to then assist with remediation of a mine site. I thought that was actually a really good story of bringing together multiple streams. So so I didn't know that you guys were doing that. I think it was really great. Are there any questions from the floor? We don't have any yet, but if we do, I will pass them on and perhaps we can come back to them after the next presenter. Oh, here we go. Harvey Allen would like to ask, what work have you conducted on the hydro and pyro treatment options after floating?
Yes, thank you very much. We are thinking of sulfatizing, like roast with sulfur or sulfuric acid, which makes the cobalt soluble to water. Yeah, maybe we are thinking of this method.
I have another question for you, Kamiya-san. In the chat, Shengdong Hang would like to ask, will you consider biological methods to extract cobalt from tailings?
Excuse me, sorry. Please tell again, please.
If you look in the chat, you can see excellent presentation. Will you consider biological methods to extract cobalt from tailings?
Thank you very much. I'm not thinking of biological extraction, but I think the UQ will do the bio-leaching test for cobalt. Yeah.
That's right. And Anita is on the call, so she can add a comment if she would like. I'm just scrolling through. We do have some more questions. Ian Wolf would like to know what happens to the rice after the leaching is done.
All right. Some rice remains, so that's a waste, but that will be waste. But we are trying to the best amount of rice to treat the acid mine drainage. But this is the rice. Some rice remains. Yeah.
And Anita has also confirmed that yes, the biological leaching is part of the UQ contribution to our collaborative project. Juliana Segura Salazar would like to ask, she says, thank you for your presentation. How does climate influence the behavior of bacteria?
Yes, but the case I presented, we are successful to treat, but in another side, the bacteria didn't work because the water temperature is very low, like 4 degrees or 3 degrees. So we need to keep the water temperature higher. So what we did is to the pipe from the tunnel to the facility is needed to be shorter to prevent the temperature of water from decreasing. So that's the solution. But
there's a lot of hot springs.
Yeah.
In Japan. Can you use the warm water?
Yeah, if we have near the facility, we can use.
And the second part of Juliana's question, is there any additional maintenance required in this type of bioremediation system?
Yeah, if some the metal sulfide precipitate in the reactor, so sometimes we mix or mix the reactor for water to go. Yeah. It is needed
to keep the reactions working. Yeah. One more question from Harvey Allen. Do you have a target copper or cobalt grade for your flotation step before roasting? And do you think, or we'll do first part of the question first.
Yeah, but that's not great. But our target is to recover 70% of cobalt. No, 70% of cobalt. We'd like to recover over 70%. Yeah, that's the target.
Okay, well then the second half of the question is, do you think 65% recovery would be enough for the project to move forward successfully? So you've said you're aiming for 70. Yeah, very good. And Harvey also says, fantastic presentation. So thank you. And I agree wholeheartedly. Thank you, Kamiya-san, for joining us. I really appreciate your presence. And that was a lot of questions. Now we are missing our next speaker. Unfortunately, he may have had trouble joining us. That was Simon Michaux from Finland. So instead, we will move straight to Pak Hilman. Pak is the senior geologist for the Centre for Mineral, Coal and Geothermal Resources at the Geological Agency of Indonesia. Thank you and welcome. And he's going to talk to us about from mineral database to exploration target. So welcome, Pak, and take it away.
Thank you, Helen. Yeah, I will share my screen first. Okay. Do you can see my screen?
You can see that perfectly.
Yeah, okay, thank you. Yeah, first of all, I want to thank the organizer of this webinar. Thank you for inviting me to present in this event. So for today, I want to present the mineral, how we in Indonesia, the Geological Agency of Indonesia, to make our mineral database to go to the exploration as a basis to provide the data to exploration target. So my name is Prima Hilman. I'm a senior geologist, and also I'm a mineral database manager for mineral. I now work for the Center for Mineral Coal and Geothermal Resources in Indonesia Geological Agency. So yeah. First of all, I want to talk about the exploration strategy in Indonesia. So we in Indonesia, the government have roles in exploration. The first one is as a regulator, we set up the regulation for the mining, especially for the mineral mining. So many regulation there, but this actually we want to simplify this to attract more investor. And the second one, the role of our government is to develop and supervision of the mineral project. Actually, through the Geological Agency, we also do the exploration by government itself, and in that task, we also want to enhance our exploration performance by apply the latest technology and exploration methods. It's including remote sensing, also geochemical exploration, geophysical exploration. Also, we want to apply the new drilling technology, and also we want to enhance our laboratory technology. So the fourth role is to apply the latest technology on data processing, including how we set up the mineral database, and also we use the mineral we use the GIS to map the mineral potential mapping, to do the mineral potential mapping. And after that, we want to accelerate the exploration by give the incentive to the company, and the sixth role, if we reconcile the data of the resource and reserve. So we want to reconcile the data of the mineral resources and the mineral reserve. And the last thing is we facilitate the exploration problem solving. So that's the roles of the government to mineral exploration. So what we do is we already set up the mineral database. Actually we compile all of the data from also from the companies, because in regulation there are so the all of the companies must submit it all their exploration data to the government. So we set the data is in the form of exploration report. Also, we collect the raw data. So we collect the raw geochemical data, geophysical, and also drilling data. And we set up the mineral database that consists of this data, and as an output from that, we already have some services in the internet, but unfortunately for now is in Indonesia, in bahasa Indonesia. But if you want to look, you can look at the services here that GeoRima is the mineral coal and geothermal database, and we have a WebGIS for minerals, and we also have the metallogenic map, and also we have the one map policy. So in one map policy, we can overlaying many data, including the tenements and the forest area, and then etc. So in one map policy, we have the same source of the data, and the other output is we create the mineral resource and reserve information. We build the mineral resources and reserve information, and the third one is we do the mineral perspective mapping. So this one what will we do right now? What application are used to build the database? So actually we use Excel, the Microsoft Excel as the data entry form. So we use the macro in Excel, and then we can enter the data here. So the data will be recorded in the Excel form, and then we save the data as the CSV, file, .csv file, comma separated values file. And after we have the data in the Excel, we use because the data is the spatial data, so we use the QGIS to move the data or to export the data to the database. So the data we use the PostgreSQL database with the PostGIS plugin, and actually from the QGIS, we export the data to the database, and then to make the interpretation, we can query the data from the database with the QGIS. So in this type of system, we use most of the open source software, and only just use the Excel as the data entry. And after that, we also outputting the data to the GIS, to the WebGIS. So we use ListMap, which is also the open source system. So we can see the data in the web. So what in the database now? We have now in our mineral database. The first one, we have the geological layer. The geological layer is composed by the scale of the geological layer is for outside Java is 1 to 250,000 scale, but for the Java area we have the 1 to 100,000 scale geological data. The other data, we have the structural data, the regional structural geological data. The other one is, we have the geochemical data. Actually, not all of the Indonesia already have the data, but we already cover all the Sumatra Island, all the Celebes or Sulawesi Island, and most part of the Eastern Nusa Tenggara, and so some of the area in the West Java, and then in the north of the Kalimantan. As you see, this is the different color here. So in Sumatra, we have a joint survey with the British government, and the red one is our fund, is ourselves, our funding. We funding ourselves, and some of the area in the Sumatra also we have the Indonesia-China joint survey. And for the Kalimantan, we have a joint survey with the French government. So there's a different color here. And the other layer, we have the deposits layer. The deposit layer is the mining, is the point of the deposit or the mineral, especially the metallic mineral deposit here, as you can see here in the region. So we have the many kind of the metallic minerals here in Indonesia. And the other layer is the license area or the tenement area. So we have the tenement area all over Indonesia. And what we can do with that data? So in this presentation, I want to give the example of how to utilize the data. So if we want, in an example, if we want to search the lithium, so we come up with this geochemical data. So we retrieve the geochemical data from the database, and then after that we make some geochemical analysis. Geochemical data processing, and we can find the lithium. Where is the anomaly of the lithium? So if you can we can see here that some area in Sumatra here, in the West Sumatra, and then in the North Kalimantan have the anomaly of the lithium. And then we retrieve the geological data. After that, we query only the felsic intrusion lithology, because as we know that the lithium very probable to find in the this kind of the intrusive, the felsic intrusive. And then after that, we overlay the geological data and the anomaly of the lithium to found in this example, to found the area in this Sumatra, in the near Padang. There are some of the intrusion of the felsic intrusion, and with the area with the elevated lithium content. So that's one of the example how we utilize the data. And the other thing, after that, with the same kind of system, of the same kind of methods, and also with the data from the exploration we have done, so we can give the we can provide the public to inform to the public that we have the mineral greenfield exploration area. So we in this slide we have the mineral greenfield exploration area for based on our data. So this is based on government data. So and as you can see here we can offer some mineral here, some metallic mineral, gold, copper, chromite, manganese, nickel, bauxite, Re, and non-metallic minerals. Non-metallic minerals is especially for the quartz sand and the graphite. So as you can see here, so that many area scattering around all of Indonesia that have potential as a potential prospect for many minerals. This is one output of the database. And the other things is we also have the data from companies. So from time to time, the companies also relinquish their area. So the relinquish area, the data from the relinquish area is submitted to or give it back to government. So from that, we can also make the greenfield area. So actually, from the data from the companies produce more greenfield area than our data in government, because there are many companies in Indonesia that explore. Actually, as you can see here, so but the kind of the minerals is not so many as if we compare to if we compare here. So there are many minerals here, but from data from the companies is just a few of them. But the number of the location is more than is here, is more than in here. So that's the what we call the utilization of the database. So that's maybe not too long from me. Thank you very much for your attention. Thank you.
Thank you, Pak. I appreciate that. There's certainly a lot of data to compile, and I think we have similar systems here in Australia for compiling company data into government systems, and so it's a big job, and you get lots of different data from different people with different levels of quality and different formats. So it's a tricky thing to keep it all together. And that actually leads nicely. I'll give it a moment for the audience to ask any questions of
Question?
Go, please, Rick.
I really enjoyed that talk. I was really excited to see that you're doing everything using open source software.
Yes, I noticed that too. Yeah.
And so I was really interested to hear, did you find any particular challenges associated with that, like getting support for developing it or anything like that, or would you recommend it to other surveys? But I thought it was really exciting.
Yeah, because we lack of fund to buy the proprietary software, so we have to creative to use the open source. But until now we don't have any trouble. So because in our team we have people that can program, can do the programming for, because QGIS is using the Python. So some of our team is capable to programming in the Python. So we just ask him to because as a geologist we don't have any capability for that, but one of our team have the capability to program the. So actually sometimes we want to mimic the ArcGIS, some of the feature in the ArcGIS. So we ask him to how we can do that in the QGIS. So that our so until now we don't have any problem for the open source, I think. Yeah.
We do have some questions for you. Catherine Loke has an environmental question. How is all of this data reconciled with forest protection in Indonesia? So I guess that's asking about the overlays of environmental regions versus mining regions.
Yeah. Actually, the greenfield we offer is outside the forest area. So we already cut the area, and then the forest area is one of our layer in our layer, so that we can cut the forest. So what we offer to as a greenfield area is outside the forest area. So that, yeah.
And Alexander Takeli I'm not sure if I've pronounced that right. Apologies if I got it wrong. Thank you, Prima, for your nice presentation. My question is, what remote sensing products or sensor products are used for your project? And if you used any technology, why did you choose that?
Yeah, actually, yeah, back to the fund again. So we use the free data that offered by USGS, Landsat, and then Aster data from Japan government, and we process the data in the QGIS, because QGIS has the plugin for the for remote sensing data. So we do some we do some processing, the data processing in the QGIS. So that we use. So everything here basically we want to minimize our cost to do all the things. Yeah.
Yeah. We actually had one of the guys from QGIS as part of last month's webinar, our tool-time webinar. So so it was really great to have them on board, and I'm sure that they would be so pleased to see the extensive use that the Indonesian Geoscience Agency is using, putting it to. All right, thank you, Pak. We will now move on to Honorary Professor Lesley Wyborn, who is a staunch regular at our webinars, and so we're very, very pleased now to have her participate as a presenter. She is going to talk about OneGeochemistry, which is collaborating globally to create a fair way to find and access geochemical data online. So a really great transition from the previous talk to this one. Thanks, Lesley.
Okay, and I apologise, but I'm going to have to stop the video if I can do that. Right, okay, sorry about that. Okay, so I just want to talk about OneGeochemistry. It's an initiative where we've got a group collaborating globally to create a fair way to find and access geochemical data online and in real time. Oops. Now just let me get organised. Right, next one. I'd first like to start with a land acknowledgement and acknowledge and celebrate the first Australians on whose traditional lands we meet and pay our respects to the elders past, present and future. Acquisition and analysis of geochemical data is pervasive in the earth, environment and planetary sciences, and has been so since the mid-19th century. Geochemistry is fundamental to understanding past, present and future processes in natural systems, and it can contribute to research topics such as the evolution of the solar system, the earth, or society relevant topics such as environment, resources, minerals, energy, groundwater, geohealth, agriculture, etc. More importantly, with the UN Sustainability Development Goals, we know that geochemistry is critical to 6 of these, as I have listed here, and it's not too hard to have geochemistry wanting to be part of the others. But the issue is that data volumes are growing rapidly due to advances in instrumentation, and in response to open access policies and science demanding more open geochemical database systems, they're emerging and breeding, as we sometimes say, like rabbits. There's just so many emerging, but there is little collaboration between the systems, and often there is competition with web portals for who has the most eye candy and pretty pictures. We need to access these global stores, but currently there are no agreed standards, and it's an absolute pain to access and merge data from them. And so we need these silos to seamlessly come together to harness the wealth of geochemical data in support of basic and applied science. So the vision of OneGeochemistry is that we will create a global geochemical network that facilitates and promotes discovery and access of geochemical data through coordination and collaboration among international geochemical providers. We envisage it as a distributed architecture where geochemical data are available globally using web services from the host data sets. To do this, it requires that the international community come together and agree on the standards that will enable fair geochemical data from participating providers to be fair. And here I want to emphasize, because it's really bad what's going on with fair. There are so many systems that are called fair and they're nothing but, they're not. To be fair, you have to be machine readable, and you cannot be machine actionable, readable, whatever term you want to use, unless there are agreed standards. The quest for these distributed architectures is not new, and I want to take a few slides to give some unknown credit to the minerals exploration industry in Australia, because their input to an inquiry to mineral exploration in Australia in 2003 highlighted problems in gaining easy access to pre-competitive information, and it was listed as one of 4 major impediments to exploration. It described in Australia existing information as incomplete, fragmented across 8 government agencies, each with its own management system and structures. And it noted that the disparate systems led to incredible inefficiencies, causing higher costs, reduced effectiveness, and increased risk occurred by the industry and its service providers. This was the input to this. And so in response to this, the government released in 2004 this response to the Minerals Exploration Action Agenda, in which it called for Australian government, state and territory geoscience agency, professional associations and industry to cooperatively develop and implement nationwide protocols, standards and systems that provide internet access to and effective storage and archiving of industry and government exploration related data. And thanks to this thing, we had the project in AuScope and also some wonderful help from industry at that time. And so we did it. And in 2005, we created one of the first examples of web services in the geosciences using geochemical data from each of the geological surveys. Each agreed to map from their internal service stores to this agreed schema, which is here in this middle part. And from that, the services took over. I think now we talk about APIs. This is nearly 20 years ago. But what you could do is go to this border in the Musgraves, which, as you know, is in WANT, South Australia, and download the data set, and it was combined, ready to go. You could actually pull down and download individual data sets. And we also worked with one company, I think it was Fractal Technologies. I have to go back. And they developed a service based on this government industry. And we saw some excellent examples of that happening the other day in the what is happening in tool time with how some of the service providers are using the GSQ API to do a very similar thing. But unfortunately, this only lasted until 2008, when feedback, well, it just was too hard for the surveys to maintain this infrastructure. It was too new. And so everyone switched back to Excel spreadsheets and file downloads, which meant if you wanted to get that Musgraves data set, the onus went back onto the user, and the user would get 6 CSV files, one from the NT, one from South Australia and one from WA. And then you get this, the GA versions of those as Excel spreadsheets for each state, and you then had to combine. So disappointing and all as it was, it did have a light at the end of the tunnel, because some people who are thinking of doing this for geological map data in the International Union of Geological Sciences saw this wonderful exemplar that had come out of the minerals exploration industry and developed this test bed for OneGeology, and that still exists today. It survived. And if you actually look at this map in this portal, it looks deceptive, but all the data are coming from each of the individual countries. They each provide and serve up their data, and it means that you get the latest data as it is made available. It's not like where you have a product and the product is downloaded and then, you know, a few years later is updated. You always access the latest information. And we've seen other exemplars of it, and there are plenty. So this is the digital network for seismological stations, the Climate Earth Systems Grid Federation, crystallography have a framework, there is GBIF, and as I'll come back to later, IUPAC stands for the International Union of Pure and Applied Chemists, and they have started to really standardize their data online and produce these standards that enable online merging of data set and accessibility through web services. And so if other domains have done this, why has geochemistry failed so miserably? Well, I can give you lots of answers, but let's not go into them. Let's just look at our current state. So our current state for geochemistry access is multiple human readable systems. They may be advertised as fair, but they're only fair within that system. When you go into it, all the data has to be loaded into it. And the reason it's not working is because we don't have agreed standards. There's a developing state, whereas I'll show later, some of the major databases have started to come together and see if we can get agreement. The future state is that there are no boundaries, and because we're all agreeing on minimum variables and agreed standards and vocabularies, we should be able to combine these data sets online, just as we did in the test bed in 2005. So the important thing is that OneGeochemistry is not building a single database. It's not human readable portals with dashboards and fancy tools. It's not a single global centralized geochemistry system, nor is it a system of systems. It's building a framework that will enable networking of multiple global distributed databases that can be accessed by machine reading interfaces or APIs. But we can't do this until the community comes together and defines the minimum common variables for each geochemical data type and technique, and we have agreed vocabularies and ontologies. But the community is starting to get it. And this is a snapshot of papers that are out there. But my first, well, not gripe, but comment is that they're not working really together. They're just setting their standards. So they work for each type, but if you try to combine different types, you're in trouble. And I guess another gripe might be that where are the Australians? There are a couple of Australians on some of these, but there's not overwhelming participation. And so we started this OneGeochemistry, and I have here the groups that are now collaborating. And Australia is represented by AusCope and the AusCope Geochemistry Network. Its twin in Europe, European Plate Observing System, is involved, as well as these major databases such as Diggers, EarthChem, GFZ, and GeoRock. But if we're going to go global, we need urgently to engage the global south, because we're only really engaging the global north. And as you all know, there's heaps of geochemical data. If we want to look at these global patterns, we need to be able to get them. And if any of you have any contacts in these other countries that we could contact, or you yourself would like to join, please contact us. But in going global, we're going to say there are no parachutes, no helicopters, and no parasites ordered here in increasing level of obnoxiousness. That is, we want to participate with these countries, but work together, not just grab what they've got or parachute in and out and not listen to them. As they say, we're not going to have colonial science. And we're also not asking these countries to cough up their data so we can store it in Western databases. It has to be, as we did with OneGeology, a global network from in situ access. And so we need to come together to meet the required standards for this to happen and the minimum variables and best practices. But we also need to develop a governance of the network, as well as a governance of the standards and best practice that makes geochemical data fully AI ready or fair. We are now just been announced that we're part of a successful EU-funded project whereby geochemistry is now one of 11 case studies, and we're starting on 1 June. And the idea is that the project will develop the features of core interoperability frameworks that work across all these, so that geochemistry can also contribute to interdisciplinary areas such as ocean sustainable delivery, agriculture, biodiversity, because we all know geochemistry is part of this. And as I've said, we actually, the 11 case studies are divided into themes. And so the beauty is that OneGeochemistry is in the same theme as chemistry. And chemistry is so far ahead in defining and making standards machine actionable that we will be able to leverage all the work they've done on the periodic table, and also with nanomaterials, with identifiers. So there's a lot of work we can do there. But also, as I said, if you look at these other groups, you can see the ones that we can now seamlessly, hopefully, integrate geochemistry data with. And the important thing is geochemistry is an ecosystem, and we need agreed standards from in the field to publication. And I'd like to highlight some of the work that's being done by the OzGeochem network in Australia, funded by Ozscope. And they note that more than, considerable percentage of data just does not end up in the public domain. Only about 10% of it does. And so if you develop a system where you're capturing the data from the laboratory, it's going to be more effective and QA/QC'd as it calibrated in the laboratory. And this proposal would be in line with what is recommended through the Australian Code for the Conduct of Responsible Conduct of Research. And if you want more information, Alex is here, so hopefully he'll hang around for what used to be drinks. But anyway, hopefully he'll hang around. You can talk to Alex because this is the Ozscope Geochemistry network. And you can join it on these websites. And they also have a wonderful YouTube channel with all their latest work. So in conclusion, OneGeochemistry is not a single database, dashboard, or a system of systems. It seeks to address an urgent need to define the building blocks for a global framework, including minimum core variables, vocabularies, machine readability of data, particularly for validation of data in publications. It is focused on it being fair, findable, accessible, interoperable, and reusable by machines and humans, and for use in modern AI ML techniques. But above all, whilst OneGeochemistry seeks global sharing of the data through community-led standardization, it still needs to allow for deeper domain specialization and innovation, the development of new techniques, and the constant improvement and evolution of existing techniques. So if you want to join, you've got my email address, and these are the other main participants in it. Contact any of us. This is an invitation to participate, and let us know if you want to be part of it. And that's it. Thank you.
Thanks, Lesley. And there are already comments in the chat asking for your contact details right before you put those up. So I'm sure you will hear from a number of people. And thank you so much for that presentation. Alex has shared the link in the chat if anybody is curious, and has also reiterated that he's available for questions. So does anybody have anything that they would like to follow up with Lesley before we move on? I was wondering myself, Lesley, while everybody's thinking about their questions, I was wondering if you had been in touch with the data analysts and data scientists at the Geological Survey of Queensland.
Yes, they've got an invitation for me to meet with them. I think it's next week, and I'm extending it to Alex. Alex, I forgot to tell you, you're going to have to come along as well. No, they've contacted us. They got wind of what we were doing somewhere else. So yeah, it's with pleasure, because we'd love to be able to connect with the GSQ geochemical databases. And I think, oh, what's his name? Tang. Oh, sorry, I've forgotten his first. Sorry?
Joseph Tang.
Joe, right. Sorry,
Yeah.
Joe. Apologies if you're listening. Joe applied to join the AGN as well. So it's all happening. The Australian Geochemical Network.
All right. There's some more. Oh, Alex has shared some more stuff. So anyone that's interested, please get on board and be part of this global collaboration. We do have one question in the Q&A. David Crosswell, who was definitely very much involved in the GSQs, setting up the GSQ's new data systems, He's asking, what do you think is the single most valuable deliverable from the project?
Okay, so again, the most valuable thing will be if we can get agreement on what are the minimum variables. If you describe an argon-argon data set or a uranium-lead or even a major element or elemental chemistry, what are the variables that you want to describe? And then once we've got those, then we can piggyback with the International Union of Pure and Applied Chemists, because they've got a lot of standardization already there. But at the moment, the community can't seem to come together and agree on, what are the minimum variables for defining uranium, lead, argon, all of them. And as I said, compared to what's gone on in other groups, it's pretty amazing how far behind geochemistry is.
Thanks, Lesley, and thanks.
And I'm a geochemist, so I can say that.
Rose Turnbull from GNS in New Zealand has put in the chat, very exciting initiative and one that New Zealand can easily contribute towards with our PET lab database. She's asking, what is the long-term viability regarding ongoing funding to maintain such an initiative? Because often geochemical databases are not maintained long-term.
Okay, so my first argument is try and cut down on the number of them, because there's too many being formed, and a lot of them are web scraping off existing databases. So they have no sustainability, and it's often hard to know who is the genuine quality analysis, right? So that's why we're saying start at the laboratories. But the long-term funding, that's what we're hoping by being invited to be part of. CoData is part of the International Science Unions, that we're going to get it up in highlights that this is a valuable data set to the UN Sustainable Development Goals. And once you get the value across, then funding will help. But equally as well, I think we should, as a community, try and cut down on people creating yet another one. And the other thing too with the sustainability is, as I said, part of the reason why the web service failed in 2008 was because the onus went on to the data providers. The costs were with the data providers. Whereas when you just deliver heaps of Excel spreadsheet, the costs is on the users, because they're the ones that have to munge it and make it go together. So it's a matter of that change being accepted and agreed to.
All right.
Okay, is that any help?
I think so. One more question. David has followed up with, in what form is that expressed? So that obviously goes back to his previous question of, hang on, let me scroll down. So what form is the valuable deliverable expressed?
Not quite sure what you mean by do you mean the standards or?
Yeah, so how will that be delivered? How will that look like?
Okay, so again, that's the other thing too that we're picking up from these other more advanced communities, in that they have a website where the standard is actually available. It's version controlled. And so when you put out a data set, you reference the version of the standard that you used, so that if you then come along with a subsequent, 10 years later, another data set, it has the standard for that year. You can compare the two. And the methodology, believe it or not, was actually developed by crystallography in 1995. So there's nothing we're proposing that has not been done somewhere by another scientific group.
All right, thanks, Lesley. We might move on because we are a little bit behind, but obviously a great topic to generate lots of discussion, and Alexander is putting more information in the chat if any of you are interested. Now, we've got some great news. Simon Michaux has joined us. We missed him a little bit earlier, but it can be tricky with so many different time zones. So we really appreciate him being able to join us. And we're going to quickly cut to Simon now before we then move on to Kari afterwards. So thank you, Simon. Simon is the Associate Professor of Geometallurgy at the Geological Survey of Finland, GTK, and he's going to talk to us about assessments of the physical requirements and minerals to globally phase out fossil fuels. So take it away, please, Simon.
Hello, everyone. I do apologize for getting my time zone reversed. Sorry, Rick. Okay, let's get underway. So can you see the presentation?
Yes.
Okay. And the sound is okay? We're good?
Yep.
All right, rock and roll. So I'm going to talk to you today about the outcomes of a report that I released last year in conjunction with some work I'm doing now as the follow-up work. Assessments of the physical requirements to globally phase out fossil fuels. Before we do, I'm going to get into what GDK is. I work for the Geological Survey of Finland. We've just recently reformed our strategy. We are now working across multiple new frontiers. Geology is our science and it is our tool set. So these are our divisions. We've got mineral economic solutions, which is your conventional exploration group. You've got geophysical solutions. Circular economy solutions is the part I'm part of, and they're attached to anything mineral processing and recycling. Energy and construction solutions, information solutions, which is we're collecting a lot of data. That the presentation that just finished, my colleagues at GTK would very much appreciate your thoughts. But we've been collecting a lot of data for some time, and there's databases which are all publicly available. There's water management and environmental solutions. The phrase we are now working to is for Earth and for us. We are operating in an area which I've not seen. This is the first time I've worked for government. Before it was either academia or private sector. So there's geoscience information, which provides and gathers a lot of information and then puts it in a form that's accessible to members of the public as well as private sector corporations. We're doing a lot of science and innovation. It is not research in the same way I saw at the SMI. It has a different flavor to it. And we're doing a lot of customer solutions. So we actually seem to have this sort of, we're between universities and private sector in our own ecosystem, but we're all moving into the same innovation systems. So this is Mintech. Mintech is a pilot plant that has a feed range anything up to 5 ton. And your typical size can be anywhere from 20 ton to 300 tons, with the record being 15,000 tons. So this is and we're in the process of digitizing this group. So we've got a dedicated process laboratory and dedicated characterization laboratory. So we are able to measure samples as they come in, and we're connected to labs to do things like assays. We've got our bench scale process lab. Now, we're not a comminution outfit. They don't do size distribution very well. In fact, one of the plans for me is to actually fix that, but they do very well on things like flotation, gravity, and magnetic separations. We've got a dedicated automated mineralogy lab whose sole purpose is to measure samples and characterize them that are going through the pilot plant. We're attached to a chemical assay that, so we've got the fast turnaround time for samples coming out of the pilot run can be characterized and turned around as fast as humanly possible. We don't have to wait. There's a lot of data coming out of the process system, and we've got our own tailings disposal dam. We've got this humongous sample handling facility that can actually blend and homogenize samples or mix samples according to a blend. Anyway, so this is what we're sitting at the moment. There is an effort at the moment to digitize and modernize this. This is what the facility looks like from the air. So this is what the pilot plant looks like. We're in the process of installing a whole lot of instrumentation, new flotation cells from Autotech, a new process control, and there is a move afoot to have a machine learning net collecting information into a data lake and harvesting what it all means. So it's a remarkable place to work, and it is a fertile ground for me to work on. So that was GTK. Within that is this work. So this report was actually released last year. The purpose of this work was to start the procedure to work out how much minerals will we need to feed the gigafactories of Europe. That was the original mandate, and it became very apparent that certain things were just missing. Excuse me. So what I did was I looked at the physical tasks done industrially by fossil fuels, what was done globally, and then determined the useful scope, the scope of useful work done with the understanding there's efficiencies to everything. I then assembled the non-fossil fuel systems that could do useful work. Like if we were to knock everything out and replace them with renewable systems, what would they be? Summed them all together in the numbers that they needed to be and calculated the quantity of electrical power needed to come off the grid. And now that we got that, we can estimate the number of solar panels and wind turbines needed. So if we expand the same energy mix as 2018 as an assumption, I determined how many non-fossil fuel power stations were needed. That assumption was not practical, and a more practical study is underway now. So in this report, we have the number of vehicles by class, number and size of batteries, an understanding of when you would use a hydrogen fuel cell and when you'd use an electric vehicle. I did estimates for the rail transport system and the maritime shipping fleet for both fully electric propulsion and hydrogen, and estimates to phase out fossil fuels of things like power generation of gas and coal. I looked at the feasibility of expanding the nuclear power plant fleet. That's an obvious answer. Can they help us? The answer is no. And the feasibility of expanding global biofuels. And again, that cannot be expanded very far either. I also looked at plastics and fertilizers. So all of that is in one place, which is why it's so long. Sorry about that. So the conversation went something like this, like how would what would it do to replace the existing system? When we look out the window now, the number of cars and trucks that you see, if all of that was electric, what would that look like? And in theory, that is a point in our future. There are debates about when that would be, 50% done by 2030, or 100% done by 2050. They're the numbers being thrown around. But so we'll have a period where we have a ramp up, where we are going to apply substitution systems as fast as we can. And then there's going to come a point when the full system is replaced. And from that point on, we will have conventional economic growth, or so we would like to believe. And so I'm going to study this point here. And so then the question is what does fossil fuels do for us? How many cars and trucks do we need? How many new solar panels, therefore the minerals that are in those solar panels? And the question at the bottom of all of it is what quantity of minerals will be needed? So it started, I worked for a geological survey, and they wanted to know their demands for exploration. And so, well, we started with, well, this is our endpoint. You know, this is the metals in the different systems that we're going to need, and then work our way backwards. And that was the plan. And so along the way, you end up sort of finding about, you know, how big is the system, and what do these systems do, and like what distance does each of these systems do? That tells us how much electrical power we will need. And then from that, we've got, well, the quantity of, if we make an assumption on energy mix, we can start talking about how much of this will have to be solar panels, and how much of this will be wind, and how much will be nuclear, and so on. So the calculation arc went something like this. What was the true scope of tasks to phase out fossil fuels and completely replace the new system? I looked at cars, trucks, rail, maritime shipping and aviation. The United States had the best data. And so did it for the United States, the European Union, China, and the fourth calculation was the globe altogether. And so everything was summed together as a global system. And that gave us the number of units that we need and a prediction. So to put this in context, in 2018, which is this is all based on 2018 data, 84.5% of global primary energy was still fossil fuel based, right? And less than 1% of the vehicles were electric vehicles. So the vast majority of the system has yet to be constructed. And as it's yet to be constructed, it cannot be recycled. So if we actually need metals to do this, it has to come from mining. That is something that the Europeans are not entirely happy with. And one of the things I looked at was the required power storage, stationary power storage buffer. For wind and solar are highly intermittent, and we need a proportion of power buffer. And at the moment, that's flagged to come from battery banks. That's the elephant in the room. If you couldn't be bothered reading the report, just read this black square. Current plans are not large enough in scope, and the task before us is much larger than the current paradigm allows for. The baseline calculation went like this. The global fleet of vehicles was estimated at 1.4 billion. That's a conservative estimate. The real number's over 1.5, I believe. And they traveled 15.87 trillion kilometers in the year 2018. Now, for this, I was able to compare all systems electric vehicle versus all systems hydrogen. And, and what came up was the electric vehicle battery mass, the mass of the battery was 3.2 times the mass of the hydrogen fuel tank in the equivalent system. So that means for the same energy storage, a hydrogen fuel cell will last 3.2 times longer or go 3.2 times further. However, you've got to make that hydrogen. Hydrogen is an energy carrier, it's not an energy source. So that hydrogen cell system would require 2.5 times the electricity to make that hydrogen compared to charge that battery. So what that means is all short-range transport should be electric vehicles. So passenger cars, commercial vans, delivery trucks and buses, anything that is within a city and has a range of less than 100 kilometers. We're talking about 65 terawatts of batteries to do that. Now that, all other studies I've seen have gigawatt hours of batteries. This is terawatt hours. So my numbers are very different to others, but no one's been able to refute what I've put up yet. All long-range distance transport should be hydrogen fuel cells. So we're talking about the semi-trailer, Class 8 HCV trucks, what's left of the rail network and the maritime shipping fleet should all be hydrogen. And we will need 200 million tons of hydrogen annually. So here is the EV fleet. Those vehicles went that distance and we will need that power to charge those batteries. And industry, we will need to knock out gas and coal, heat and building heating and steel manufacture. We will need that power. The hydrogen economy, those vehicles require that amount of hydrogen and we will need that amount of power to make that hydrogen. I looked at biomass. Now, the biofuel could be the only way to keep the aviation industry going, or the most sensible way. And it could be the most sensible way to keep the plastics industry going. And it also might be the best way for a fertilizer industry. So then the question is, well, how far can we push it? And we actually need a sustainability audit with new assumptions behind it to actually look at how far can we push that, because it's very clear that the planet cannot produce enough biomass to make the biofuel alone to replace petroleum, not even close. So we need to know what the true limitations are, and that is actually someone else's, that's another piece of work to attend to. So let's put the power together. So we will require 37,670 terawatt hours of extra power. Now, if we looked at the same mix as 2018 and expanded it up, we're talking 220,000 new power stations of average size. Now, to put this in context, the existing fleet is about 46,000. Now, that is reflected by the difference in energy return on energy invested between fossil fuels, oil, gas, and coal, and new systems like solar and wind. They're just not that strong. In fact, they may not be strong enough to replace fossil fuels. So here is the mix that the first study used. So wind and solar are highly intermittent and they vary. We need a buffer. At the moment, that buffer is the gas industry. Take the gas industry away, we need something to replace it. So yeah, so in the literature, they've got as much as we need 12 weeks supply for the whole system in buffer to get through winter for wind and solar. And some of the estimates are down to 1 month. but for the whole system. I've used 4 weeks just for wind and solar alone. And that's actually a very conservative estimate. But if we took that conservative estimate, we're talking 574 terawatt hours of batteries. That's almost 10 times what's needed for the electric vehicles. And I'm not seeing or hearing very much discussion about that. That is the elephant in the room. If we don't fix that or address that, wind and solar won't work. So the column on, these are the numbers graphically. So the column on the left is what we did in 2018 in terms of power generation. The white is what we're phasing out. So that's what we can keep. That's what's useful. This is what we want to phase out, oil, gas, and coal. And the green on the right is what we are hoping to bring in. So we are discussing making a system substantially larger than the existing global system using an energy that's more expensive and more complex and not as effective. So the tasks are as follows: charge the electric vehicle batteries, make the hydrogen, phase out oil, gas, and coal power generation, heat buildings, especially in the Northern Hemisphere, and the tiny sliver across the top is replacing coal-fired steel manufacture. So the second generation of this study was to look at, well, here's our task. We need this extra power, 37,000 terawatts. How do we do it? I rang up the IEA and talked to them, and it turns out they are reading my reports but won't admit to it. So they said that all new power capacity, the vast majority, if not all of it, will come from wind and solar because all other systems were not going to expand very well. So the third generation of what I'm doing at the moment now is based on a report they've released where they've actually come clean. They've actually made some recommendations about what hydro and nuclear might do. But so for this generation, we're looking at wind and solar, where solar takes 30% and wind takes 70%. It turns out this energy split is, they've come up with a better one again. But if we were to do that, so look at the number of stations, we're talking about 342,000 average solar farms. And like each farm is like, you know, installed 33 megawatts. And we've got this massive buffer storage. It's huge. And so, all right, so now we're going to work out what metals are in these units and how much do we need. So, all right, we've looked at the metals. And for each of the battery chemistries, what's in each one in terms of kilograms, kilograms per kilowatt. And we've also got now an estimate in the year 2040, what they think the market will be in terms of different chemistries. Taken 2040. It's very dangerous predicting the future. It almost never works, but they've kindly allowed to do it, which means I can reference them. So yeah, and so we've got an estimate in 2040 what they think they're going to be. And so now we can actually ask the question, how much metal will we need to phase out fossil fuels? So we're going to make all the necessary electric vehicles, all the EV batteries, hydrogen fuel cells, like the platinum in each one, the wind turbines, the solar panels, and the power storage batteries, all together. And you often hear this, it's just a function of market forces. As demand goes up, we will just need more. So these are the numbers of this generation of work that's come out where this is not all the metals required, but this is like 6 metals that I've picked that are probably going to be a problem. The first column is what we will need, including storage batteries. Note the units are in million tons. And copper is at the top of the food chain there. So in 2019 is the middle column of mining production. And so that's what we produced in 2019. And the third column is how many years we would need to produce at 2019 rates to hit those targets. Remember, they think they're going to do a third of this in 8 years. And so as you can sort of see, especially when we're looking at lithium, 16,000 years, that's probably not going to happen, guys. So then it's just the case of we'll just open more mines. And so, well, you know, we've got plenty of reserves going. So here's those numbers up against global reserves. And excuse me, as you can see, global reserves just aren't going to be enough. We just don't have enough. So at this point, it should be apparent that this is a crap plan and we need a better one. And it's as simple as make batteries out of something else. You don't have to use lithium-ion chemistry to make a battery. You can make batteries out of zinc. You can make them out of fluoride, out of sodium. There's stuff in our waste products that we can use. And there is a lot of things that we could do, but all research at the moment is funded towards lithium-ion batteries to the exclusion of everything else, when actually we should be looking at parallel systems. We will need them all. So just to remember, you know, I'll just go and explore for more. For every 1,000 deposits discovered, only 1 or 2 become mines. And the time to take a deposit that's been discovered that's actually okay to a producing mine is about 20 years. And for every 10 producing mines, 2 or 3 will lose money and shut down. So this is what the European Commission thinks. The World Economic Forum released a report in 2019. The column on the left is what they think if 30% of the market will be electric vehicle globally, and they think there's going to be 2,600 gigawatt hours of batteries, where my numbers, that number should be 19,556. They have seriously underestimated the scale of the task, and part of it is they've underestimated the number of vehicles and the tasks done. Conclusions: this is what we need for annual capacity. It's huge. We need 220,000 new power plants. So wind and solar is highly intermittent. Our power buffer storage, you're using a very, very conservative estimate. We're talking 574 terawatt hours. So current thinking has seriously underestimated the scale of the task. Nuclear is vital to keep industry going, but it's not viable to scale up to be a replacement for fossil fuels, and neither is biofuels. The numbers are on the ground for that now. Battery chemistries other than lithium ion should be developed, each with different resources required, and we need to develop their value chain as well, the industrialization behind those minerals. There's rejected mineral shortage to supply raw materials for battery manufacture, but also for wind turbines, solar panels, and anything else. 2019 production rates are not even close to being appropriate. 2021 reserves are not large enough either. So metals of all kinds are about to become much more valuable, and an evolution of the industrial ecosystem is highly likely. There is a coming renaissance for the exploration and mining of minerals, and I personally think Europe will be opened as a mining frontier. And that is something that is not fashionable to say at the moment, but I believe it's coming. Thank you. Questions?
Thank you, Simon, yes. Look, I'm so glad that you were able to join us, because that was absolutely fabulous and thought-provoking, and, you know, utterly needed. So thank you. Really, really appreciate you being part of our day.
Welcome.
And look, we've got questions, we've got comments. I'm completely not surprised. Mark Duffett in the chat is saying that this should be compulsory viewing for every newly elected Minister of Parliament, or in fact everybody. So I do hope that we do record the sessions, and do hope you're okay with us posting the
that's fine.
online, so that we can all share it widely. We do have some questions for you.
I talk to politicians now. I'm talking to members of Parliament, both in Finland, but also the British House of Lords and US Congress. I'm talking to people all over the world.
Well, you're going to be talking to ones here in Queensland too. So just
okay, all right, let's have it.
Bring it on. So Trevor Beardsmore is saying, Simon, do your calculations take into account increases in demand for transport, energy and the like arising from increased development and living standards for developing nations?
No, it doesn't, because the first oil report shows that we don't have enough oil in the ground to do that. The inequality is actually baked into the data. So what I've done in a very, very simplistic and brutal fashion was to replace the system as it is now. Right? If we're talking about future growth, and if we want to bring developing nations in terms of into line with, say, Germany, I've used Germany as the marker for that. There is not the physical reserves for oil or gas to do that as a proxy for energy. And so my work is showing that we've been sort of rolling along in a form of delusion with multiple blind spots. That's one of them. So, sorry.
Yep. Yep. No, it's, you know, it's a complex system to model, isn't it?
Yeah.
Mark also has another question. He's saying he's found your report. He's shared the link in the Q&A, but he's only a fifth of the way through the download. He's asking, what does scenario E, which must be part of your report, show is the rate limiting step on large expansion of nuclear power?
So nuclear
can you
power.
talk us through scenario E as well.
Okay, there are 6 scenarios. And so scenario A was just everything's electrified. Scenario B, all vehicles are electric vehicles. Scenario B is everything is electrified, including power generation. Scenario C is the hydrogen economy. Scenario D is biofuels for supplanting of ICE vehicles. Scenario E takes the power requirements of the previous scenarios and says, right, we will now source all power with nuclear. And it looks at the moment, nuclear power is about 10% of global power generation. So that nuclear power plant fleet has to not only expand, right, to be all existing power, but also to take on the renewable power requirements as well. Now, at the moment, there's 441 nuclear power plants in the global fleet, and we're adding 1 or 2 a year on average over time. Because remember, a lot of them are decommissioning and we're constantly replacing them, and most of them are actually overdue for replacement. So I actually assumed if we all got behind nuclear, if we put our worries aside and we really got behind it, and I looked at generation 3 plus, generation 2, and some assumptions around if it was generation 4, what would this look like? And if we added 25 new nuclear power plants a year, every year for this year going forward, and we had an aggressive expansion, and each power plant took 5 years to build, which at the moment it sits closer to 20, right? And so if we really got behind it and forced industrialization, and like we did in World War II, and say in America and in Europe, and how fast could the nuclear power plant fleet actually expand, and what power would they generate, and what uranium would they consume, and what spent nuclear fuel would they generate out the other end, and how much would have to go into power-cooled storage, how long would have to stay there, and then how would we split it up and dispose of it according to its classification. And the answer was the nuclear power plant fleet took 70 years to expand, and it didn't get, I think it got to about 60% of the way that it needed to get there. But what happened was all existing resources of uranium were exhausted in 70 years if we did that expansion. So if we left the nuclear power plant fleet as it is at the moment, those resources will last about 300 years before we have to even think about looking for more.
Simon?
Yep.
When the uranium price spiked, we almost got to the stage where seawater was economic for uranium.
Yeah. So
enough uranium in water to
So what's the energy return on energy invested?
That's true, yeah.
So what I did was took the World Nuclear Association reports, and they had resources like relatively assured resources, and they had speculative resources, and they had prognosticated resources and unconventional resources. So I took them all the way out to unconventional and said, right, this is what we have at the moment. How long would that last? Now, the problem is not running out of nuclear fuel, because we can go find more. The problem is the nuclear power plant fleet cannot give the power needed fast enough, right? Because we need to take fossil fuels offline now, and we needed, like, say, a nuclear system operational, say, in 4 or 5 years' time, if that was to work. The real problem, too, is the massive stockpile of spent nuclear fuel, which will require power to cool for some of it. And that's where the headaches go. So now, on the other hand, nuclear is the only way we can actually support heavy industry, like concentrated doses of power that can be done anywhere in the world in any weather. Right? No other power system can do that. And so we will need I estimate the nuclear power plant fleet will have to double in size. That's an estimate to maintain our industrial requirements going forward, but it cannot be the magic bullet that does everything.
Okay, we've got a few, oh my gosh, we've got increasing numbers of questions, and we're pressed for time and Kari's waiting, so I'm going to ask a couple of them quickly. John Menzies has made more of a comment than a question. While there are a number of alternative battery concepts, the one unifying element is copper, so transporting that energy to where it needs to go, and that cannot be realistically replaced.
Yeah, true.
Yeah.
Like a wind turbine has a copper cable as thick as your leg connecting that wind turbine to the grid. So if you have an offshore power wind turbine, the cable is longer.
Yes.
So,
the tropical part of the globe is unsuited for large-scale solar and wind. Should your study consider different global characters?
So what I've done is a very, very crude calculation based on numbers that the World Economic Forum and the International Energy Agency have put out on the existing system. What is obviously going to happen is society is going to be reordered and reconstructed around a new energy reality, right? So we are not going to do this. This is the thing to show that what we are planning on is impractical and something else has to take its place. That something else is going to be the subject of work by all of us, I hope. So should we look at different geographic regions and their climate? Absolutely. Should we do things differently? Absolutely. All the battery alternatives that are out there, there's lots of them, but when it comes to funding, getting funding and industrialization off the ground, everyone's put their collective hat on lithium and lithium-ion battery chemistries. And it's very difficult to get anyone to take you seriously beyond a theoretical discussion. That has got to stop. So, and on it goes.
I can tell you that the Queensland government is very committed to vanadium redox flow batteries because we have no lithium, but we do have vanadium. All right.
How much
Mark,
vanadium do you think you need?
That I don't know. Perhaps you can tell.
I can. In fact, I've just done a, let's see, as we speak right now, good grief, look at that. I'm actually doing the next generation of this work, and it's what you can sort of see on the screen here. Let me just, so this is by battery chemistry, and this is for the electric vehicles. So this is 1 million tons of what we will need. But when we get down to, hang on, or further up. When we get to stationary storage, stone the crows, look at that vanadium, 872 million tons.
There you go.
Million tons of vanadium metal. That's not ore, that's not dirt, that's refined metal.
Yeah. Well, there you go. Like I said, you'll be talking to the Queensland government shortly. Mark Dufford has made the comment that China is punching out nuclear reactors in less than 5 years. So perhaps that sort of forced industrialization. And I am trying to speed us up because we are running late. And John is making the apology to Star Trek fans, specifically Rick Valenta, that he forgot the copper can be replaced by plasma conduits. But anyway, there we go, and Simon. So let's move on. Thank you so much, Simon. I'm so glad that you were able to join us, and, you know, absolutely wonderful to have you on board and have such a thought-provoking talk.
Now I see why you're too busy to work out the time difference between Finland and
absolutely.
Yeah, look, it's been a while before I live that one down. Sorry about that.
Yeah, totally. And for the audience, Simon used to live in Brisbane, so he should know what the local time is.
I used to work for the JKMRC and the SMI, so I should know. Incidentally, I'm coming back to Brisbane for a work trip sometime September, October this year.
Okay.
If all works out. And I'm going to come and see the SMI because one of the things that, and the GSQ, I'll come and see anyone. And so I can present to anyone, I can talk to anyone, we can workshop with anyone. I'm doing a lot of workshops, roadmaps that are put together very quickly. And I've got my fingers in all sorts of pies.
Excellent.
So
we will catch up then, and if you can hang on the line, we will have a more open, free-flowing discussion session.
No problem. No problem.
Finished. Thanks, Simon. And now, Kari, thank you so much for your patience. Really appreciate it. And you've been here since the start of the session. So again, thanks for hanging in there. And I hope that we now have your name right. Kari Aslaksen Lesley. I probably pronounced it awfully. I'm sorry.
Okay.
Kari is the head of the Mineral Resources section at the Geological Survey of Norway, NGU, and she's going to talk to us about the role of the Geological Survey of Norway and what we do and what is the mineral potential of the NGU, or of Norway. So please take it away, Kari.
Thank you, Helen. And I hope you can see my presentation now.
Yes.
Yeah, good. So good afternoon, everybody. And apologies for my sore or my rusty voice today. I'll try to speak anyway. So yeah, good afternoon, everybody. And thank you for the organizers and also for the previous presenters for very interesting talks. And thank you for giving me the opportunity to present the Geological Survey of Norway and talk a bit about the mineral potential in Norway. Although aggregates and construction materials actually represent the major part of the mineral resource industry in Norway, I will focus on the mineral resources today. NGU is the national expert agency for issues related to the Norwegian bedrock, mineral resources, soil and groundwater. And we strive to be relevant to fill the society's needs for geological data across a range of fields. We are an agency under the Ministry of Trade, Industry and Fisheries in Norway. And we are highly research-based and believe we must be so in order to provide the quality of data which are needed for modern society. One of our tasks is generating data to understand the Norwegian mineral resources and serving these data through national databases and products, and identification and documentation of potential for mineral resources in Norway, in collaboration with universities, counties, and developers. Let me see. Yeah, so we are mapping and we're working on.
Can I just interrupt? We're seeing your actual PowerPoint file.
You are?
We're not seeing the slides.
Oh, just a second. That was strange. Now?
No.
It's still the same? Okay.
Still the same. Like we're seeing, you know, the menu and the note.
Yeah, I see.
Really...
What about this one?
Yes.
Yeah, good. Okay. Yeah, so we're mapping and working on a variety of scales. We're collecting data from on Norway, from air and from space, and of course we're mapped on the ground. We have a well-equipped laboratory to assist us with this data collection, and also targeted mapping and investigations which covers, for instance, mineral resources, landslide hazards, water supply, environmental management, land use planning, marine planning. The backbone of the survey responsibility is expressed through our national databases and our map services. And the most relevant for exploration and assessment and understanding for the mineral potentials are bedrock databases, the geophysics, petrophysics, geochemistry, and of course the mineral resources, including the construction materials. We actually have 30 national databases in total at NGU, covering the themes from groundwater to geohazards, marine seabed, and to mineral resources. And we're not only the national repository for geological data, but we also have it for samples and for drill cores, all of which we make available for the industry and for the public. We have a facility outside of Trondheim in Norway that holds more than 700 kilometers of drill cores. And exploration companies, industry uses these facilities to log both old and new drill cores, and we're quite fully booked at the moment, actually. So this is a screenshot of our mineral resource map service. And upgrading information in our databases is a continuous process, and we'll still work to improve the data coverage. NGO aims to provide better and more useful data, not only for exploration, but also for land use planning and resource management. And this means, for instance, that mineral resource information has been analyzed and graded into the categories for deposits, prospect, provinces, and occurrences. In this respect, we term everything we can confidently quantify as deposits. Areas which contains anomalies, such as high density of showings or other indications, and where we cannot estimate size or potential, we term prospects. And wider areas in which we know may host certain deposit types, we term provinces. And our occurrences are still generally presented as point data. For mineral deposits, we also provide an assessment of the importance. Code compliance is not an issue here, as these data are meant also for aerial planning and must contain all we know. So we grade deposits into national, regional, local importance based on a given set of criteria, such as in situ value, but also national or international criticality. And we are also now modifying our databases to include a UNFC classification. Our map service also show the location of drill cores in the survey archive. And this not only include the exploration, as you see as red dots in the map here, but also drilling for infrastructure and other drilling conducted by this survey. We are now quite ambitious with our machine learning capabilities, and we try to employ machine learning in predictive mapping, not only for mineral resources, but also for lithology to see what we missed on the ground. So this is a matter of combining the data that we have, various geophysics, density, observations, mapping, and geochemistry in a systematic way. And our laboratory is an important tool. The most recent additions relevant to exploration and resource geology is our hyperspectral scanning station, which is in operation. We are employing the equipment to both marine and hard rock cores, and the facility is designed for mobility, so it's we can take it to the places that we want to log. And our ambition is to scan and document all the drill cores at our drill core center. Our laboratory collaboration with SINTEF and NTNU in Trondheim is called MIMAC. It's also in full operation with a new multi-collateral facility in action at NGU, and we have access to other high-end equipment such as microprobe and MLA at NTNU. So we would say that all in all, we have a well-equipped and strong laboratory targeted at the geological analysis. NGU has a strong collaboration with some of the Norwegian counties, which also helps to boost the data collection. And data originating from these programs have recently or will soon be released on a variety of commodities within these counties. We just finished a large program in Trøndelag, in the central Norway. The central Norway contains a large part of our major historical VMS type copper zinc mining camps. And we targeted some of these more insufficiently mapped BMS areas with new mapping and characterization. And we also worked with intrusion hosted nickel and carbonates. And a new program is starting now for 3 years, where we try to increase the knowledge about the mineral resource potential in the county of Møre og Romsdal. We're going to look into the iron, titanium, vanadium resources, among others, and also carbonates. The survey is involved in the pan-European mineral projects, such as the FRAME project that was finalized this spring. That was a part of the ERANET project, a package of ERANET project called GeoERA, aimed at mineral resources and was hosted by the European Geological Service. FRAME dealt with various resources, and some of which are battery critical metals and minerals. And as you can see at the European map of unknown occurrences deposits here. The GeoERA raw material project is summarized in a newly published monograph that you can find. And all the European projects are usually aligned with the national strategies, and we have ongoing data collection and focus on these metals. So this is the current EU criticality list, metal and minerals that are a risk to Europe, either due to supply risks or because of our economies relies heavily on them. And this is a factor that, one of the factors that NGO is using when prioritizing our work. And the list has expanding, and it will probably change again. And if we had made a list now with a new situation in Europe, I think we'd have another table actually. And several of these critical materials are very much alive in the Norwegian geology and production, like the natural graphite, silicon, titanium. And based on this report, a list describing the situation in the Nordic countries was published last year. This was a collaboration between the Geological Service and in the Nordic countries. And the new mapping project initiated by NGO the last years is of course based on this criticality list. So we have VMS projects where we try to gain some new data and maps for critical minerals. And we also recently started a project on nickel and apatite with rare earths. So a major difference to the Nordic countries when it comes to Norway is that the current Norwegian production is strongly biased towards industrial minerals, with almost 30 mines and quarries in production. That's the green dots on in the upper right map. The production is dominated by calcite and dolomite marbles of a variety of qualities and application. And quartz is also extracted in large qualities. The active mines also includes Europe's largest producer of nepheline cyanide and the graphite, and the world's largest producer of olivine. And what this map doesn't show is all the aggregate quarries that we have in Europe, and we actually export quite a lot to Europe. The map to the right shows the most important, to the left, sorry, shows the most important metal mines and projects, and the active metal deposits include titanium and ore at Telnes and Ørtfjell. And there is care and maintenance production to the very north in Sydvaranger. So Sydvaranger is here, and we have Telnes down here. Telnes is one of the only 3 or 4 hard rock ilmenite deposits in operation in the world, and the largest titanium producer in Europe. And it provides 5 or 7% of the world titanium raw materials. The ore body is basically a noritic intrusive body carrying around 28% ilmenite, and is located in the Rogaland or North-Side province. And iron is produced in Mo i Rana by Rana Gruber. And it's one of the very late but historic iron formations. And there is a compliant resource estimate of more than 500 million tons of ore. I've also included the Skaland graphite deposit here, but I will return to that along with the other advanced project a bit later. So we have the Engem, and the advanced project is the blue ones in my table here, not in production yet, but we have the Engebø rutile deposits and the Nuster copper deposits, and also the Sydvaranger banded iron formations. I will also talk a bit more of some of the more less mature exploration projects that are listed in red in the table. So copper and zinc mining constitutes the historical backbone of the Norwegian mining. And most of the production came from volcanic deposits in the Caledonites, where the last mine closed in the 1990s. But the copper mining seemed to be restarting again in Norway now. There is sediment-hosted copper deposits in basement windows in northern Norway. And Nussir in the Repparfjord tectonic window is the most prominent deposit discovered. It's actually the biggest copper find through time in Norway, and deposits contains resources close to 80 million tons. If we should point to one or a few metals which Norway is particularly prospective for, titanium would definitely be one of them. We know of about 300 different deposits, and I've already mentioned the Tellnes deposits that are in production. We have two types of titanium deposits in Norway. It's the Proterozoic massive type, anorthosite provinces, and in some of these, ilmenite is accompanied by vanadium and apatite. And in the Caledonites, we have Mesoproterozoic titanium-rich mafic rocks, which have been exposed to eclogite-facies metamorphosis during the Caledonian orogeny. This process has led to the generation of a string of hard rock rutile deposits, like this Engebø titanium deposits. The rutile deposits will give you lower titanium grades with a higher quality titanium raw material. The Sydvaranger deposit is a 2.6 billion years old banded iron formation in the very north of Norway. It was mined continuously from 1910 until 1997, and again from 2019 to 2015. From 2016, the mine has been operated for care and maintenance with a minimal staff. A new mining concession have been awarded and accepted by the company now. When it comes to graphite, the Taro deposit is currently the world's highest grade operating flake quality graphite mine. It is also the largest flake graphite producer in Europe and the fourth largest outside of China. The Geological Survey of Norway has been working quite intensely on a regional scale through many years, and has defined a number of additional possible targets through both geophysics and ground surveying. And this has enabled companies to better target exploration and development. And geophysical and geochemical geological ground follow-up work was performed in the region with some support from the hosting counties. And we also did some short hole drilling. And some known deposits and some new discoveries were studied in detail. For instance, the Bukkemon deposits, which was EM surveyed on the ground, sampled and analyzed, and finally modeled. Norway is prospective for rare earth elements, and the Fen carbonatite is the REE deposit in Norway, but also on REE in igneous, but there are also REE in igneous apatite in various places in Norway. In Fen, NGO has been working closely with geological advisors to the hosting counties who is the real expert on the carbonatite. And we have been involved and contributed with various geophysics and short-hole drilling in the mapping project. The Fen carbonatite is a classic locality and the home of the carbonatite nomenclature used at the globe. It has been mined for iron and niobium, and actually also phosphate. However, today the Fen complex is primarily interesting as a host for rare earth elements. In 2018, the Norwegian government asked NGO to drill 2 long drill holes into the carbonatite to confirm the exploration potential of the carbonatite rocks. And all available data was compiled to delineate areas with mineralized carbonites. And the areas which you see in green on the right comprise coarse-grained ferrodolomitic carbonatite enriched in RAE, sorry, primarily through RAE-bearing fluorocarbonites. One of the drill cores extracted contained an average of 1.7% total of rare earth over a core length of 716 meters. 1.7 is not enough for a mining operation, so an exploration company needs to find and constrain a mineable resource. But the prospect is there. The project is now being developed by a company that has extensive drilling program at the moment. We've had, when it comes to phosphate, we've had some minor production in Norway back in time, but I think today Siilinjärvi in Finland is the only European producer of phosphates. But there is actually a handful of targets in Norway, including Fen, as we talked about now, and Kodal, and others up in the north of Norway. But I would like to talk about the Bjerkreim-Sokndal deposit here today. It's a layer intrusion and what was an academic project through the last half of the 20th century. And in the late 1990s, the NGO geologists became aware that some of the layered sequences are really high in apatite. We later worked together with the industry to map and constrain the apatite-rich zones, and it became clear that we had resources here where apatite, ilmenite, and vanadium-rich magnetite together make up more than 30%. The deposit has actually been passively claimed for many years, but some years ago, Norge Mining came in strong, and they have improved the geophysics, and they have sampled and drilled extensively. So here we are also quite happy with the role that we have had at the survey. We haven't seen the Bjerkreim-Sokndal as an important asset, but it took a bit longer for it to get interested than we hoped for. So with this, I would like to thank you for the attention. I hope to have given you a brief look into our activities in Norway, and that you found it interesting, although we cannot, or compared to Australia, we are quite at a much smaller scale. So please feel free to contact me and my colleagues at the Geological Survey if you want to. Thank you.
Thank you, Kari. I loved watching your talk because many decades ago when I did my PhD, my field area was in Norway, and it was around that anorthosite in the Egersund area. And I was looking at the metamorphism of the region and more than the economic geology, but still, it was a nice trip down memory lane to see those rocks again and hear you speak about them. And I do remember seeing a lot of the titanite, rutile, all caught up in those high temperature reactions. And I think that intrusion was, I think it came in at about 1,000 degrees. It was a very high temperature intrusion from memory.
Yeah, I don't know the intrusion in detail. That might, I think you know it better than me, actually.
Yeah. Anyway, it's a fascinating area, and I don't think Norway needs to worry about comparisons to Australia because, you know, it's a brilliant place to be a geologist, I think. Now, do we have any questions for Kari while she's here with us?
I had one.
Go for it, Rick.
I'm just interested to know whether you're seeing, what level of exploration you're seeing in Norway. I mean, it seems to me that the amount of activity, the amount of mining activity relative to what you see in the rest of the sort of colledonides in terms of mineral endowment and mining, that maybe that there's a lot more potential. But I'd be interested to hear if you're seeing an increase in exploration activity, or whether that's been, whether it has been really well explored, or what.
Well, it's definitely not well explored, and I think we see a trend now that is a lot of there's much more interest. But still, there is not the activities is not as big as in our neighbors countries like in Sweden and Finland. But it's increasing, and as I said, it's at our core logging facilities. It's fully booked now, so there is hope. Yeah, and we also see that the authorities has put more focus into minerals, at least we'll see it not in actions yet, but at least in words. So we're hoping.
Definitely. And then you were mentioning that if you had put out the critical metals list now rather than a few years ago, that it would look a bit different. So what do you think would be the major changes on that list, given the political situation in Eastern Europe?
Oh, I think it's well taken into account Simon's talk as well. I think it would be changed quite a lot. Yeah, but of course, both Russia and Ukraine delivers a lot of important resources to Europe. Ukraine is a huge producer of titanium, for instance, and others. So yeah.
And does that create an opportunity for Norway to step into that gap then, particularly with the titanium?
Yeah, absolutely. But still, it's that takes time to develop new project, and so and Norway is not known for the processes are quite slow in Norway when it comes to the permits. So it's not easy to open new mines in Norway, unfortunately. Not yet.
So what I would say is the CRM maps that are I've been part of those groups to make those maps, and they look for the past 4 years of what has been a supply chain problem. They're not looking to the future at all, and they are not prepared. And so most of Europe has not been surveyed below 100 meters in terms of ore deposit discovery. There's been a lot of geological mapping done, but not ore exploration. And so there's multiple world-class deposits here. And one of the things I do to my students is I give them a deposit, say 50 grams a ton, that's been found under Cologne Cathedral, and tell them to mine it. What has to happen. And so, but the entire Nordic frontier, Finland, Sweden, Norway, is geologically very strange. It's amazing, the stuff that you see here, but there is a lot of mineral deposits here that you don't see elsewhere in Europe. And so there are opportunities incoming for all technology minerals right across, and the geological surveys will be required to step in and lead this, because it'll become apparent that we will need minerals and we will need mining. One of the projections being made is global free trade will break down, and it won't be free, and it won't be easy to do. So we can't depend on materials flowing in from China anymore, or Russia, as it turns out. And so we have to become more self-sufficient, and the ability to do this and to get on our feet will happen sooner in the Nordic frontier than it will with the rest of Europe. So the geological surveys across the Nordia frontier have an opportunity on their hands, and mines will open when the people trying to keep them closed can't buy the next iPhone.
Yeah.
And watch things change very quickly.
That's it. All right, thank you, Kari and Simon, again. If you do have any questions for Kari, please put them in the chat or the Q&A and we can come back to them. Now, we did have on our schedule Garth Graham from USGS to give a recorded presentation, but we've actually got Roger Hamburg from the Geological Survey of Sweden, who's been patiently waiting for his turn. And I was wondering, Roger, if you would like to go before we do the recorded presentation, just because you've been patiently waiting for so long now.
Yes, of course, I'm ready, so I could go.
All right, well, let me give you a proper introduction. Roger is a geoscientist with the Geological Survey of Queensland. His area is mineral information and the mining industry. And he's going to talk to us about mine waste management at the Geological Survey of Queensland, which is something that Geological Survey of Sweden. Oh, it's getting later at night here, so obviously not with it. But I was going to say that that's a subject that we're spending a lot of effort working on here in Queensland. So very excited to hear what you've got to say. And I will tell the audience as well that Roger accepted our invitation to talk because I found him just by total chance on LinkedIn. He popped up in my feed and I was like, oh, that would be perfect. So I sent him a message completely out of the blue and he very, very kindly accepted. So thank you for that, sincerely. And over to you.
Yes, I'm going to have to share my screen. Hopefully it will go on to presenters mode. Now it's all right.
Yep.
Okay, as Helen gently said, she was invited me on LinkedIn and I was quite good to get that notice. So I'm very glad to be invited to this seminar. As Helen told you, my name is Roger Hamburg. I work as a geologist at the Geological Survey of Sweden, and today I'm going to talk about the mine waste management that we do at the survey. But first, sort of a brief introduction about the survey. We're about 300 employees, and we are situated at 5 different offices in Sweden, with our head offices in Uppsala. I'm actually situated in Luleå, our northernmost office. So we are some geologists, geophysicists, and hydrogeologists, and more. So the main areas of our work is to work for a sustainable use of soil, rock, and groundwater. And for that matter, we are conducting some geological survey to be able to facilitate urban planning and also exploration, of course. And we're also gathering and strengthening the geological research. And another target or another aim is that we work for to ensure that Sweden's environmental goals are achieved, such as a non-toxic environment and a groundwater of good quality. We do some extensive monitoring of the groundwater levels and groundwater qualities around in the countries, and also we are doing some analysis and research about sea sediments as well. And we have, of course, a drill core archive that we are very proud of. It stores about 4 kilometers of drill core also with a core logging facility. But something that we also is doing that we are very prominent work area is that we are maintaining our superfund mine sites. Actually, there are some mining companies that didn't have the economy to do the rehabilitation of these sites, and then we as a governmental organizations we have stepped in and take the responsibility for those sites. So one of those sites is a test mine, which was in operation in just 10 months. And we have done some rehabilitation actions on that about 5 years ago. And the budget for that was about $10 million. And another one is the Aslaksen mine, which is known as the biggest environmental catastrophe regarding mining in Sweden. It's much of people are talking about the Aslaksen mine when they are speaking about environmental damage by the mining industry. And there, the remediation actions is ongoing as we speak. There are 4 open pits that are currently filled with either backfilled with inert rock material or backfilled with groundwater. When we're also about to cover the waste rock deposit, and we have installed a lime station that you can see in the upper left corner here in the picture. And the budget for that is about $40 million. Then we have the Aslaksen mine. That is a mine that we have had the responsibility for about 24 years, 25 years actually. And the Aslaksen mine was a copper mine closed in some 45 years ago, and we have done some rehabilitation actions. The most ones was done at about 25 years ago. And we have also done some evaluations of these measures. So, but when we are talking about mine closures, and in Sweden we often talk about different kinds of covers. We speak about dry covers or wet covers. So when we want to cover our mine waste so that we can hinder oxygen to penetrate into the mine waste. We also use a method called raised groundwater table, where we divert surrounding water streams so that we can maintain the mine waste fully water saturated. And we do that, of course, we want to reduce the oxygen transport down into the mine waste. Because we want to hinder that acid mine drainage is to be formed. And if you remove the oxygen, you remove also a big part of the acid mine drainage. But we have also performed some evaluation of the mine closures that has been conducted in Sweden, both by ourselves, but also by the other mine operators. And as we can see that these mine closure actions, whether or not they are successful or unsuccessful, there's always a need for complementary actions. The mining company or the mine operators always need to go back to the sites and do some additional measures, do some complementary actions to enhance the measures that already has been done. But in time, these mine closures has grown better through better regulations and better knowledge as well. But still, there is a lack of waste characterization conducted and a lack of water balances analysis conducted to be able to predict the future quality of the leachate coming from these sites. These predictions are seldom performed, or they are performed in the beginning of the action itself, but then it's not reviewed afterwards. So the issues for the mine company is, when could we leave the site? When is the water quality and leachates, when does it comply with the stated demands from the legal authorities? with no further actions? When could we release the water directly from the mine sites into the environment without any actions, any water treatment or anything? And we often talk about the time perspective of 30 years for that. But we're going to look at the Aslaksen mine, which was a copper mine which left a lot of tailings with high contents of arsenic, zinc, and copper, with the high contents of pyrrhotite, which is very acid potential mineral. And we applied the dry cover on that tailings pond some 25 years ago, containing of a clay till with a very low hydraulic conductivity. But we also performed some other actions, such as we constructed some calcite barriers and some drainage ditches and some calcite ponds as well to be able to treat the acid drainage. But what could we see from the effects of the quality of leachate when we are looking at from the rehabilitation actions and forward in time? So we look at some sampling point where we see that the situation back in 25 years ago, the metal contents was quite high. The leachate was quite acidic. But when we are looking at the present situation, you see that the metal contents is still quite high, and the still acidic waters that we are talking about. This is something that you want to see a sort of a steep decrease of metal contents in these waters, and then they are stable at lower levels, or at least low level, but that hasn't not happened here. So what could be the conclusion of that? Could be a long-term wash-off of this oxidized tailings, or could it be another source for these metals? That we can see from the other sampling point, where we're also having high contents of metals within this point, and an acidic pH in the leachate, and we can roughly see the same. And there is still high metal contents in the leachates even after about 25 years. So again, this is not something that we want to see. We want to see that the actions have better effects, and that we can release the water back into the environment quite soon. Because we want to know when could we leave the site, when could we stop treating the water. And as for now, we don't know that. We have not any predictions that says within 20 years or within 30 years we can stop the water treatment, we can shut off the area and leave the site. But looking at the other mine, the Svartträsk mine, which was quite a small mine, where we have large contents of namely zinc and an acid forming waste rock in this way. We perform some actions there as well. We have backfilled the mine waste into little pits where to be able to treat the upcoming water in this case. And we also apply the sealing layer with a very low hydraulic conductivities. Another actions we conducted or constructed is a lime station and some drainage ditches. But we also, in this similar case, we don't want to see the effects of the rehabilitation measures. what's the effect on the leachate quality. And this is something that we can see here, the situation back in 2015, prior to the soil cover, the metal contents in the water was very, very high. And this in the water as well. But as you can see that the measurement was quite varies a lot, because we haven't measured the water flow in this sampling. So, but you can see that there's a development that it's going downwards for at least. So the situation nowadays, or present times, that is that we have quite low contents of at least cadmium and nickel, but still there's a lot of zinc in the water, and the pH is still quite low. And it will take some time before we can reach the limit values situated that I stated here. So the same here is, when could we leave the site? For now on, we have no good predictions about could it be another 25 years or 50 years and so on. So for some final remarks is that regarding the Adak and Svarträsk mines, we're missing a lot of analysis of waste characterization prior to these remediation actions. We're also missing a water balance. With those analyses, we would be able to have some predictions about the future quality of the leachate. And then we might know a little bit better of when we can leave the site. But a positive thing of the data set at Adak is that it's really long term, so we can follow it back from 25 years and until now. And that is something that we were continuing to take in samples from this site to really see about the long-term effects. So, but what could we do to enhance the future mine closures? And this is something that quite common in Sweden and quite common in other countries as well. We need to do more planning. We do need to do better predictions with analysis of the waste characterization and water balances within our mine sites. We also need to conduct some evaluations we need to know the function of these covers, so they are as promising as they should be. Do they hinder oxygen and water transport? Could we follow their effects or follow their development? And we need data for models of this oxygen and water transport for long term. And also one thing that we need is we need to have those predictions, but then by continuous evaluation, we go back and we revise these previous predictions and we make new ones, so that we all the time we will have some fresh predictions, so we'll know a little bit better of when we can leave the site, when the water quality is so good that we can let it out to the environment without further treatment. So that's what I was going to talk about waste treatment. I was only to toss in a project that we are having right now in the survey. We are examining mine waste potential source for metals if we can perform remining with our mine waste. And for that matter, we have a sampling campaign that's quite extensive. We take a lot of samples. We do geophysical measurements on our tailings ponds to be able, maybe to be able to correlate the water saturation level in our tailings, and maybe to correlate metal contents in our tailings with geophysical analysis. And for that matter, we are doing some analysis, obviously, and we are having some discussions with the industries to have their continuous input in this. But we have done such analysis or such sampling campaign before, and we can see that there's a lot of metals in our mine waste in Sweden, but with this project we can enhance that data quality, and hopefully I could present some results in the next year. So that was all for me. Thank you.
Thank you, Roger. Really appreciate that. It's great to see the different approaches to not only potential valorization, which you just touched on at the end, but then how long does it actually take to remediate a site? When can you actually responsibly walk away from it? And that's a big question, and not one that many people think of, I think. I know I've got a couple of questions for you, but I'm going to hold on to those because there are several from Anita Paweka-Fox in the Q&A. So she's saying that some of the most stimulating work that she's seen in the cover space for mine waste has been the use of alkaline wastes like green liquor dregs from other industries commingled with mine waste, or used as a direct cover. Lulia had investigated this and undertaken a field trial about a decade ago. Do you know if this research thread is continuing?
Yes, it is, but we have a research project application to the research fund and agency here in Sweden, but unfortunately that was denied. But the research is still going, so we're looking to have models of these covers by the means of oxygen and water transport. So that's something. In this autumn, I'm actually going out to the site of Svarträsk to install some instrument over there with the cooperation of the Luleå University in Luleå. So we're doing a little bit of a cooperation outside what to say? Yeah, outside
of funding. Yep.
Yes.
And Anita would particularly like to know what are the outcomes now after many years of that research, and how is the green liquor drag performance?
Now, there has been a research project in the south of Sweden with green liquor dregs, and I haven't heard any negative effects, that it's still ongoing and that it's a good performance of the green liquor dregs, but the green liquor dregs is a waste. So when you're talking to the paper mills and telling them I want a specific quality of my green liquor dregs, they might not be that interested in sort of providing you with that, because it's a waste and the production goes first. So if you're producing a lot of paper and the green liquor dregs becomes to have some certain quality, that's it. So they don't produce green liquor dregs for the mining industry. They sort of so that's a problem with quality insurance about the dregs.
So can you speak to what would be next in the innovation of alkaline waste products within your research groups? What do you think comes next for that project? Say you got funding, what would you do with it?
Well, I think it's all about what I told you about it. It's about evaluation of research, long-term research, setting up long-term research programs about mine closures. Up till now, there's very few of them.
Yeah.
So one of them is Geovic in Canada, but there needs to be more of those. So setting up a long-term program would be my first priority.
Okay. Anita's next question is in terms of the remining or reprocessing opportunities. She noticed that cobalt isn't on your list.
It's going to be there.
It's going to be there. I would have thought in that style of deposit you'd certainly have cobalt. And then she's also asked if you can elaborate on the geophysical methods that you've chosen to use and explain, what the benefits or limitations were of what you chose. I noticed you had an electrical conductivity cross-section up there, and we've been trialling geophysics on tailings as well. So curious to know what you chose and how it worked. And
that is not my line of expertise, but I think for now we use most of the most common techniques to be able to see what correlations we can do, and we are doing some drilling in these tailings ponds and in these facilities, storage facilities overall, to be able to see okay, what could be the best technique to use.
I think we used Loop EM, and if I know Lauren and Anita are both in the audience, so they can correct me via the chat if that's not right. Loop EM, but then other people also proposed IP, induced polarization techniques. So
I know we're way over time, but can I ask a question?
Oh, please.
It's been a really interesting set of talks today, and all the way from all the mineral supplies we're going to need, how short we are, and just a whole range of different things. But it was really interesting to finish with your talk, Roger, because we're in the SMI doing, one of the things we're doing is looking at what we're calling complex ore bodies, which is ore that's locked up. You look at copper, think to Simon's 9 billion tons of copper we're going to need, and we've got 1 billion tons of copper locked up in deposits we can't access right now. And people say, how could that be? And if they watched your talk, they would know it's because you, as the government, are stuck with old mines, trying to rehabilitate them so that they don't leak heavy metals into the surrounding countryside. And people don't want old mines that leak heavy metals into the surrounding countryside, and therefore they don't let the mines open. So my question, though, is how did you as the government end up having to rehabilitate these mines? Did the owners walk away or go bankrupt, or
Yes, the owners went bankrupt. Actually, I looked at the remediation plan of one of those mines that I presented, and they predicted that the cost for rehabilitation in one of that mine was to be $100,000, and that's 10 years ago. And now the budget for the mine is, the Blaiken mine, is $40 million, and it's not going to stop there, I think. So it's going to be higher, I think. And that is something that people need to know. if the mining company that don't behave, then it's gonna cost, of course. So
I had one comment that I was going to make, but then I think we're running so long now, and I really appreciate all of the audience sticking around to hear these fantastic talks. The one comment that I was going to make, which I think Anita Parbecker-Fox would make if she was one of the panelists, is that there's a case for characterization of potential waste. So even as far back as the exploration stage, understanding what the mineralogy and the chemistry of the rocks is in a complete way, so that you know not only what are you going to be digging up and producing, but then what are you leaving behind, not just in terms of the bulk commodities, but the full suite, so that modelling can start very, very early on about what the waste is going to look like and what's going to be required to look after it and remediate it.
yes, I'm aware of that, but the status of those works right now, that hasn't been happening.
No, but hopefully we can change that moving forward.
Yes.
Simon has just shared a link in the chat for a survey of end-of-life finish industrial battery metal sites that have the potential acid mine drainage impacts. So that links in very nicely to what you're talking about, Roger, as well.
Yeah, thank you, Simon.
All right, thank you so much. You've been here since the very start, so that's coming up to 4 hours now, and we are nearly an hour over time. So we do have one final presentation. If those online want to stick around, please do, because you know this talk, it will go for I think about 28 minutes, but it represents a tri-national collaboration between Australia, Canada and the US. It's going to be delivered by Garth Graham from the USGS, but we do have Dave Houston online from Geoscience Australia, who is also involved in the project and he's been hanging in for a long time as well now, so he'll be there to answer any questions if they arise. So please stick around. There are some more questions in the chat, and take it away, please. Rick's going to run the recording for the presentation. Thank you so much as well, Roger.
Can you see the can you see the screen?
Yep, I can see it. Yep.
Okay.
Well, good afternoon, everybody.
Sound okay?
My name is Garth Graham with the USGS, and I appreciate the opportunity to talk to everybody today at your workshop about the Critical Minerals Mapping Initiative, which is a tri-national collaboration among Australia, Canada, and the US. And whatever I talk about today is trying to describe what CMMI is. However, it's obviously been the work of a lot of different folks from GA, GSC, and the USGS, and others. Turn off my camera so you can see the slides. So today, my goal is essentially to cover what at least USGS views as critical minerals. Talk a little bit about CMMI history and background. Kind of approach of what we've been doing as this tri-national exercise, and then talk a little bit about ongoing and future directions. Really, future directions. So, first of all, this is the definition of a critical mineral based on the USGS publication, NASA, and 4TA. And the key point is that critical minerals are minerals, elements, or substances, they're not just minerals, of economic or national security interest. Key thing is that supply chain for getting these minerals is vulnerable to disruption. That could be from foreign political risk, non-favorable trading partners, etc. And then, of course, the absence of these particular commodities would have a significant consequence in terms of economic or national security for the United States. Importantly, note that fuel minerals such as uranium and water and industrial minerals are not included. So I stole this slide from paper Emsbo, Lawley, and Sarnoda, and the key things here is that critical minerals are really important in everyday life. So we see there's an electric car there, there's a military aircraft, there's a tablet, wind turbine, and just to put it in perspective, you know, for the batteries, the modern wind turbine has about a ton of rare earth elements in it, for one wind turbine. Then, you know, jet contains half a ton. So electric car batteries, 60 kilograms of lithium, you know, and tablets. Our phones have things like 75 different critical minerals. And when we mine these things, of course, they can either be main products, co-products, or byproducts, and many of them are byproducts. One of the things that is important about critical minerals distributions across the globe is it's not uniform. So the green countries shown here, the diagram is essentially illustrating, you know, what commodities that are on the critical mineral list come from what countries. And while Canada and Australia, United States produce certain commodities, significant market share of them, the key things to note is, in particular, China has essentially the edge of the market in a whole host of different critical minerals. So that kind of leads to us all wanting to be able to have access to commodities in the events that there's political instability. And turns out, this is a slide from Al Hofstra that he presented. So it might be a little bit out of date, but essentially, Australia, Canada, and the United States have very similar lists for critical minerals. There's something on the order of 39 if you don't break out the rare earth elements as individual elements, and PGEs to treat them as a group. But so we have tremendous overlap in our interests. So that kind of brings in the focus of the Critical Minerals Mapping Initiative. And on the right there is an open file, or excuse me, a fact sheet published by Karen Kelly in 2020 that kind of summarizes what this initiative is. All three countries are friendly countries, and we have interest in being able to promote critical mineral discovery in all three of our countries. We want to be able to better understand the contents of ores in Australia and North America. Then going a little more onto the research side, determine the geologic controls on critical mineral distribution in the mineral deposits. And then, of course, identify new sources through the critical mineral potential mapping. And so far we've touched on many of these aspects to some degree. The project structure. The first meeting was in December of 2019. So there's actually been a lot of success that has come out of this. USGS started a pilot program in, what was that, fiscal year 21. Several publications have come out of this. We'll talk a little bit about the portal, which is a first of its kind concentration of high resolution geochemical data from ores. And then there's publications like data-driven prospectivity modeling by Lawley, McCafferty, and others, which was just published this January. But so now a little bit of structure, and there'll be additional publications. I know that David Houston is working on a couple that are associated with CMMI as well. So the structure, we have an overarching steering committee And then we have working groups, essentially looking at fundamental research. Another one working with modeling, and then communications folks. And I'm going to focus particularly where the red box is. So there's the deposit synthesis team. We'll talk a little bit about that. Data team and the portal team, the folks, the GAs that are so instrumental in getting this stuff put out publicly. And then in the modeling group, essentially it found what I'm calling foundational data or base data. That'd be geologic, geophysical, deposit type information that we can use for prospectivity modeling. Then there's data-driven modeling team, and overlapping with that is a knowledge-driven modeling team led by Josh Coyne and Mike Gadd from GSC. So our current activities, we've done a lot of work on deposit synthesis and now finalizing system types. So we have to come up with an agreement across all three organizations of what are we going to call something? How do we classify something? And we incorporate this into the geochemical analysis of ores. And so essentially, we know for any given sample, what deposit type is it? They're working on how to classify the systems. So there's no inconsistencies across agencies. And thus far, we've had data provided from GA and partners, GSC and the USGS. As you'll see, it's about 7,400 samples. It's high quality, multi-element geochemical data for well-characterized samples. So it's not just any sample that gets thrown in there. And the key thing, as I'll mention again, periodic updates are expected. Then there's another group that is working with the geochemical data to interpret it. So we already have this first slug of data, and I'll mention a little bit about that. Then the base layer development or foundational layers for the modeling. And so that's incorporating geologic data, deposits, prospects, geophysical data. And then we also have added on to that working with paleoreconstructions and relationships of deposit formation at discrete time periods. And then there's the actual modeling folks that pull this stuff together. The data-driven part led by Chris Lawley is done, and the knowledge-driven prospectivity modeling, as I mentioned, is ongoing now. All right, so starting off the deposit synthesis, last year there was quite an effort to do deposit classification schemes for critical minerals. And this publication came out by Al-Hafsha, Vlad Lesley, and others. And essentially, this is really important. Standardized classifications, again, across all three countries. It's applied to CMMI, or the Critical Minerals and Ores Geochemical data set that is hosted on the portal. And the neat part about it is it permits evaluation of this geochemical data on a level playing field, right? So we can look at relationships among deposits, deposit types. It's supposed to say potential research avenues, and of course identify data gaps. So where do we need more information? So one of the questions that we're working on is mineral system. This is the broader picture of going from energy source, transport, trap, and outflow. You don't always make a deposit, but you can have a mineral system that is functioning in the general area that is responsible for one or more different deposit types. And so that is the aspect that is still being hashed out across by working group within CMMI. So now we're looking at the geochemical data. This is the portal, and you can see the web addresses that you can use to get to it. It's online, fully accessible, and we have lots and lots of samples from there. And just to look at it a little easier, each one of the red dots there is a sample location. And like I said before, it's about 7,400 samples in the database today. It is going to be periodically updated, probably semi-annually from various sources. So that would be the government agencies like the GA, GSC, USGS, state agencies. I believe that there's some discussion of getting some data from Queensland incorporated into this. And of course, academia and industry. And that's one of the things that we'll note is that we don't always, the national surveys only have so many samples, and it'd be great to get additional samples from other people to really start to build this out. So now, within that database, we have started a working group that is dealing with analysis. And the objectives of this are essentially to characterize the data, what's in there, what's missing, what needs to be cleaned up, identify patterns and trends in the minerals. Now that we have this nice deposit group and subtype classification scheme, when we can start looking at variations in critical minerals between different districts or even individual deposits, right? Or different subtypes. So one of the things we might find, since companies typically don't publish anything other than their primary commodities, that there are enrichments that we didn't even know existed simply because we didn't have this nicely consolidated data. And then one aspect that is real world is that there are mixed data methods in here. So the USGS, for example, does 60 element sodium peroxide sinter analysis finished by CP. Others might have, some of the data might be 4-acid, so you get different concentrations, apparent concentrations of metal. And with this, we can identify knowledge gaps, areas that we have lots of gaps, and you may have seen on the map. That's fairly obvious just from the data points. But currently, we're assessing base inosite, zinc, lead, IOCG, IOAs, VMS, and porphyry epithermal groups. This is just being an example of data. I believe you can actually do some of this type stuff, not in this format necessarily, but directly in the portal. But this is something that George Case pulled out in IOGAS, and it's an example of hematite versus magnetite dominant IOCGs, where concentrations are normalized to upper crustal abundance. And so purple is hematite dominant, and then the more orange yellow is magnetite dominant, and we can see that there's quite different trace element signatures associated with these. So now we can start to investigate what's going on. Now, in terms of what I call, in this case, baseline data, but this would be that foundational data that goes into modeling. This is just a screenshot. On the left is the open file that shows the data sets to support the data-driven modeling effort that Chris Lawley of GSC put out. So this is his data cube on the left. That's the cover for that file. And on the right is a work in progress by the USGS, where we're taking those data and making them into individual GIS layers, and also generating other derivative products, specifically dealing with things like geophysics, different types of geophysical analysis. And that is essentially in review. It is a tome. I think it has something on the order of 42 layers, I want to say. And some examples of that are shown right here. And so some of these base layers, they'd be magnetics, MOHO depth, satellite gravity. We can see then there's the LAB, the stuff that Corral worked on with Hogarth and I think David Houston, for example. And all these different layers can be then fed in and assessed, for trying to help to locate, what gives us the best signal for mineral occurrence locations. There are, in that case, I showed North America. There are many other products that are also for Australia. It's just hard to show all on the same plots, but these would be some examples of maps that Anne McCafferty worked on with the folks at GA. Another kind of baseline data set that we're trying to add is paleoreconstructive modeling. And so on the left here is just a screen capture of from G plates. And that's a present day model provided by Bruce Eglinton of the University of Saskatchewan and David Evans from Yale. And sitting underneath that is actually a horizontal gradient map for shifts in the depth of the LAB, just as an example. But the goals of using this type of a tech approach is to understand metallogenic events in this kind of tectonic and temporal context. To identify, potentially we can extract some of these things out and identify new prospective areas. Ultimately, we want to relate this to critical mineral endowments. In some cases, like for byproduct critical minerals, we're actually not looking at the primary commodity. We're looking at the primary commodity and not the byproduct, and then we have to ultimately relate that back to endowments of, say, something like germanium or gallium in a basin-hosted deposit. So currently focused similar to the folks looking at the data sets in the portal. We'll start investigating basin-hosted zinc lead, VMS, porphyry epithermal, and IOCG IOA groups. So in terms of modeling, the initial focus that was picked was basin-hosted zinc lead deposits. And for the data-driven, we looked at both CD and MVT deposits. That's kind of a useful place to start because I think all three countries, certainly Australia, has significant basin-hosted lead-zinc deposits. Like some of the biggest, the premier. And then Canada also does, and of course the US, the big one we have is Red Dog. So there is a common interest right there. That's a deposit type that is shared everywhere, and same for MVTs. So this is a great opportunity to get everybody to work together, and we built essentially seamless maps or standardized maps so that we don't have 4,000 different geologic units just in the United States, but we simplify the geology and we can look at it through time. And ultimately, this kind of model can help address major unanswered questions. Yeah, data-driven modeling is actually done. The slide is from last year. Like I said, Chris Lawley published that. I think it was in January. It was formally out. The knowledge-driven prospective modeling is happening right now, and it takes a little more effort because we had to get people together and try to get expert knowledge. So notice right now, unfortunately, zinc is a critical commodity, at least from the USGS's perspective. But the studies have not yet assessed things like byproducts for, say, gallium, germanium, or indium, where we might have to start looking at critical mineral to major element ratios. Say, if we think it's in zinc, ratio and the concentrations of these in our portal data to kind of get a rough estimate of these commodities in ores. So an interesting thing that fell out of Chris's work is that now we're talking a continental scale. On the right there is a diagram, the principal component analysis of Canada, Australia, conterminous US, and Alaska, and you can see that there are different criteria that weigh really heavily, more or less, for different types of deposits. And so apparently what we really have, I like this slide because it shows that there are similar, probably geologic processes that would be nature that are impacting rocks with a somewhat different history, which would be the nurture. So just an interesting observation. This would be an output from one of the figures from Chris's work using a gradient boosting method for prospectivity modeling. So this, again, is the data-driven approach. So we display different critical mineral study areas here, if you will, or sub areas, across all 3 countries. And what it highlights in the more yellow is areas that are most prospective. And as we grow our database, we'll be able to understand more about the byproduct critical mineral potential within these deposits. These are MVTs that I'm showing right here. So the knowledge-driven approach for CD deposits, okay, we actually use an entire workflow, and we figure out ore system elements, things we need to know, sources of ligands, the transfer processes, sources of metals, fluid drivers, basin architecture, traps. And what we have, the snapshot on the right, is just showing, for example, for fluids, we know that we need brines. So what kinds of things would tell us that we would get brines? We could have evaporites, we could have carbonate shells, we have paleolatitude. Okay, well then those are theoretical things. Then the question is, what would be the proxy for that? Lithological descriptions, for example, or plate construction models could help to address things like the evaporites or the paleolatitude. And then we have to figure out, we had ended up scoring these things as a group to see, well, which one of these parameters or things we think we can actually identify in our maps, in our data layers, and then use those scores to generate what's the knowledge-driven approach for the deposits. And schematically, that'd be shown with something like this for a given pixel. You have geologic data, you have geochemical data, you have geophysical data, and then combining all these different data sets, then we can come up with, hey, based on what we know here, and based on our input, the basin looks right, looks like it was deep enough. We're going to make that a highly prospective area. And so that would be the red dot on the far right. And one of the questions by comparing the data-driven and the knowledge-driven approach is, will we get different results, and how do they differ? Moving forward, one of the key things that we need to do is to continue to expand the critical mineral database of ores for systems and deposit types. And so there's essentially an open call out there for well-characterized samples from internal and external sources. So that would be very useful for us to have. We'll continue to investigate the critical mineral associations among the deposits and the systems. That's is fantastic that we have a standardized method we can now use across all 3 countries, and we have different viewpoints, and we can, this puts everything on a level playing field, and I think we'll learn a whole lot about critical mineral association. One of the things that we've been discussing as we look at different data sets and we try to work on this knowledge-driven approach is trying to understand, what are these geophysical signatures that we see in data? Why do they link up, at least with basin-hosted systems? What does that represent? How is that, directly or more likely indirectly controlling ore formation? So we want to also need to be able to link the commodities to critical mineral endowments through time and space. And so, for example, in basin-hosted deposits, like I said, the germanium, perhaps gallium or indium, is not the primary thing that is being produced. In fact, it's very hard to get that information. So that's why we have that the portal geochemical database. And existing prospectivity models will help with this. And then paleo reconstructions. Do we see variations through time? And so really the ultimate question that we wanted to get to, and we've only been at this really for about 2 years, you know, what in-ground resources might we have access to now? You know, and then what would we have in the medium term, and then in the long term? So I think that this has been a fascinating project, and I think there's a lot more good stuff to come. So thank you.
Well, thank you to Garth in absentia. It's a huge body of work across different countries, and it's great to hear the update of what's happening there. Dave Houston is on the line, and he's able to answer questions. So thank you so much for hanging in for so long. It has been a mammoth session, Dave.
Can you hear me?
I can hear you. Yes, yes, we can. Dave's joining by his phone. He's having some connectivity issues.
I've got one.
Go for it, Rick.
All other people think of one. I thought that Chris Lowley's diagram, the principal component of data sets that showed the separation of Canada, Alaska, the US, and Australia in terms of the data that were important, immediately made me think, well, obviously there must be systematic differences in the data that the different areas are collecting, because I don't see how the difference in important data sets could be so large. But I mean, the other thing that impressed me about the talk was just the level of collaboration that you guys have entered into now, which is, I think, really exciting. But so my question is, what, you know, you've been at this for 2 years now. Was there any really striking sort of low-hanging fruit where you all got together and said to each other, "What, you're not doing this?" or "Oh wow, you're doing this, we should do it as well," or you know, things that transferred from one country to another as an approach that the other country wasn't doing?
Okay. Okay, I'm going to just turn off my phone now, so
Okay.
I don't get the feedback. So could people ask questions in the chat so I don't have to turn on my phone again? The main thing that we found is a lot of information in large-scale geophysical data sets. And Garth talked a lot about that, and you saw some of that. I mean, the obvious thing is the LAB data, and the quality of data between the three countries is quite different. Australia has a reasonably good data set of LAB. LAB is a lithospheric asthenospheric boundary, and some work that we did early on suggested that sediment-hosted lead zinc deposits tended to occur above a contour of that boundary, about 170 kilometers. And it worked both in Australia and also in Canada and the United States. Now we've since pushed that on, and there's other data sets which basically show the same boundary. Gravity shows the same boundary. Lead isotopes show the same boundary. We also see the same boundary in MT data, and in this case, it's the boundary is shown up. The boundary is shown up as a resistive zone, not a conductive zone. So I think one of the things that we've learned is that there's a lot of data sets out there. We just have to look at them in a different way. And just look at the relationships and how they can do it, how they relate, and then also how we can understand them, what they mean. So that's been one of the things. I guess the other thing is the difference in data availability. I mean, GA or Australia, include all of the state surveys and GA, actually have very high quality data sets. Whereas the North American countries don't have quite as high quality data sets, or they don't have as much data. And there's various reasons for that. So Australia is actually in a good state in that regard. So hopefully I've answered that question, Rick. And so I'll go on to.
Yeah, thanks.
Okay, right. So Lesley has a question about uploading everyone's data into a central databases, or are we accessing the data sources in situ? Unfortunately, Lesley, we are bringing data into a central database, and so it's not like what you envisage. And hopefully, maybe in the future, we will design a system whereby you can just go in and extract the data from different data sets. And that's one of the reasons why we have to annually update things, and we're going to have an update probably in August. But hopefully in the future we'll be able to, as you like to do, have it where we access the data and directly, and so it's accessible at all times. The geochemical data that we model are actually accessible. You just have to go to the CMMI or CMIO portal, and you can download the data. And we do have some tools associated with that portal where you can actually start doing some modeling of the data. And I think you can bring in your own data if you want to. So hopefully that answers Lesley's question.
Dave, not quite. What I'm after is
I'll
if you are.
But are data structures and vocabularies accessible? Yes, they are accessible. There's a lot of metadata with it, so you can actually find that out relatively easily. And we've actually taken a lot of time in determining how that is set up, and yeah.
Yeah, the main thing we'd like,
and a bunch of other people have been involved in that, so it should be reasonably well set up.
Yeah,
okay.
The main
Lesley, Dave can't hear you.
I can't hear you.
Helen also asks, yes, so she asks about using the data, the mineralogical and geochemical data that we're acquiring to determine what might have been missed in mine waste across the different countries. That's one of the intentions that we have. So basically, if we know what's in the ores, and then we subtract what's been extracted from the ores, then we can actually get an indication of what might be actually in the mine waste. And so we're going to do that. Yep. Lesley, I'm gonna actually, with regards to your questions about vocabularies and ontologies, I'm gonna ask you to get in touch with Dave Champion and Ollie Raymond about that, because that's beyond my limited knowledge of databases and data sets. Ian has a, okay, I'll send around a downlink to all. Okay, I guess that's something for Helen. And I think that's all the questions that we have. So hopefully I've answered the questions and yeah.
Thanks, Dave. Hopefully you can hear us now via your phone, laptop setup. So I really appreciate you sticking in for this long to answer those questions on behalf of Garth. It's been a long session, but I think one that's been really, really valuable. And I also want to say thank you to the panelists that have held in. Some have had to leave for various reasons, but thank you to everybody, both panelists and the attendees online, for hanging around for such a long session. I think it's been really great. There's been a lot of really active discussion, which is why, you know, for some of those talks, we didn't want to stop them short because it's so great to hear about what's going on around the world. We're not going to open up for a general discussion this time because it is so late. I can hear my partner and my daughter getting dinner ready in the kitchen, and I'm sure everybody else, you know, Evan's still in the office for GSQ, so he needs to get home to his family too. So really appreciate all the effort. I want to say a big thank you to Evan for pulling all of this together. He's the coordinating presence behind the webinars now, and it's been really great to have him on board. Thank you to all of our presenters. Thanks to everyone for the lively discussion. We will make the recordings of all the presentations available. It'll be in a week or so, and that will be on the GSQ UQ webinar webpage. Just Google, I don't know if we've got the webpage up, Rick, if you can share it, but if you just Google GSQ UQ webinars, you'll find it.
Yeah.
So
I don't have it right here with me.
No, don't worry about it. We'll share it in another date. And next session, next month, we won't have a regular webinar because we're going to be holding a face-to-face plus online workshop over 2 days. It'll be held up in Townsville for those who are attending in person, but we will make it available online for those who can't travel to Townsville, and that'll be 2 days of talks. So come along to that, hear about what the GSQ and our collaborators are up to. But in the meantime, thank you so much to everybody. It's been a really, really great session, and I'm really, you know, a lot of people who have left already that I want to thank, but still thank you to those who have hung in, and really appreciate your presence and your attendance and your participation.